The universe has an edge, and humanity just touched it. 46 billion light-years from the chair you are sitting in right now, there is a boundary. Not a wall, not a fence at the end of existence. Something far stranger. A horizon carved by physics itself, where the fabric of space-time runs out of history to show us. Beyond that line, light has not had enough time to reach Earth. Beyond that line, the universe may continue forever, or it may not. And the most unsettling part is this: we will never know. The speed of light is absolute. The age of the cosmos is fixed. And those two facts together have locked us inside a bubble 93 billion light-years wide, drifting through an infinity we can never see. But here is what we can see. James Webb has looked 13.4 billion years into the past and found galaxies that should not exist. Hubble aimed at a patch of sky no bigger than a grain of sand, held at arm's length, and discovered 10,000 galaxies stacked in the darkness. Voyager 1 crossed the heliopause after 45 years of silent flight and sent back data from a place no human-made object had ever been. And at the frozen edge of our own solar system, 4.5 billion miles from the Sun, we found worlds so strange they forced us to redefine what a planet even is. This is not a story about distance. It is a story about limits, about what happens when a species builds machines capable of seeing the earliest light in existence, and then turns those machines on and discovers that the universe refuses to behave the way the equations promised it would. We are small, impossibly, incomprehensibly small, and yet we built tools that let us see the face of creation itself. That may be the most defiant thing we have ever done. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. There is an edge to the universe, not a wall you could fly to in a spaceship, not a border marked with signs or fences or anything you could actually visit, but an edge nonetheless, a limit beyond which light itself has not had time to reach us, a horizon defined not by distance but by time. And if you do the math carefully, accounting for the expansion of space itself, that horizon sits roughly 46 billion light-years away in every direction, which means the observable universe, the entire sphere of everything we can possibly see or measure or detect with any instrument ever built, spans about 93 billion light-years across. And yet, the universe is only 13.8 billion years old. That mismatch, that gap between the age of the cosmos and the size of what we can observe, is not an error. It is the signature of something far stranger than most people realize. Space itself has been stretching the entire time light has been traveling toward us. The universe has been expanding since the moment it began, and it has never stopped. This is where our journey starts, at the edge of everything, at the place where time itself began. The cosmic horizon is not like the horizon you see when you stand on a beach and stare out at the ocean. That horizon is just the limit of your perspective, the point where the curve of the Earth blocks your view. Sail toward it, and it moves with you. You never actually reach it. The cosmic horizon is different. It is a real limit, imposed by physics, defined by the age of the universe and the speed of light. Light moves at roughly 300,000 kilometers per second, fast by human standards, but the universe is old, and even at that speed, light has only had so much time to travel. Any object whose light has not yet reached us sits beyond our cosmic horizon. It exists, but we cannot see it. We cannot interact with it. It is, in every practical sense, outside our universe. Now here is where it gets strange. If the universe is 13.8 billion years old, you might assume the farthest thing we could possibly see would be 13.8 billion light-years away. That would be the straightforward answer. Light travels for 13.8 billion years, covers 13.8 billion light-years of distance. Done. Except space does not sit still. It has been expanding the entire time that light was traveling. So by the time a photon from a distant galaxy finally reaches Earth, the galaxy that emitted it is no longer where it was when the photon started its journey. It has been carried away by the expansion of space itself. Today, that galaxy sits not 13.8 billion light-years away, but more than 46 billion light-years distant. The light we are receiving right now left its source when the universe was young, and the source has been retreating ever since. This is not science fiction. This is not speculation. This is the measured, observed, confirmed structure of the cosmos. And it all traces back to a single event that happened 13.8 billion years ago. The Big Bang, the moment the universe began. Not an explosion in space, but an expansion of space itself. Everything that exists, every atom, every photon, every cubic centimeter of emptiness was once compressed into a state so small, so hot, so dense, that the laws of physics as we understand them break down completely. Then it expanded, and it has been expanding ever since. For the first 380,000 years after the Big Bang, the universe was a glowing fog, too hot for atoms to hold together. Electrons zipped around freely, scattering photons in every direction, making the entire cosmos opaque. You could not see through it any more than you could see through a wall of steam. Then the universe cooled enough for electrons to settle into orbit around atomic nuclei. Hydrogen formed, the fog cleared, and for the first time, light could travel freely through space. That light is still traveling today. It has been stretched by the expansion of the universe, redshifted from visible light all the way into the microwave range of the spectrum. We call it the cosmic microwave background, the CMB, and it is the oldest light in the universe. It is a snapshot of the cosmos as it looked 380,000 years after the Big Bang, encoded in a faint glow that fills the entire sky. We cannot see further back than that. The CMB is the edge of the visible universe in time, the wall beyond which no telescope, no matter how powerful, will ever let us see. NASA and the European Space Agency have spent decades mapping the CMB with extraordinary precision. Satellites like COBE, WMAP, and Planck have measured its temperature fluctuations down to millionths of a degree. Those tiny variations, the hot spots and cold spots scattered across the sky, are the seeds of everything that came later. Galaxies, stars, planets, you. The slightly denser regions in the early universe pulled in more matter over time, collapsing under gravity to form the first structures. The slightly less dense regions stayed empty, and from those small differences, the entire cosmic web of galaxies and voids emerged. The CMB is not just a relic, it is a blueprint. But the CMB is not the edge of the observable universe in distance, it is the edge in time. The light from the CMB was emitted when the universe was 380,000 years old. Today, the matter that emitted that light has been carried away by expansion to a distance of about 46 billion light-years. That is the cosmic horizon, the farthest place from which light has had time to reach us. Anything beyond that horizon is, by definition, unobservable. Its light has not yet arrived, and depending on the future behavior of the universe's expansion, it may never arrive. The horizon is not fixed. It grows as the universe ages, but it grows slowly, and the expansion of space is accelerating. Objects near the edge of the observable universe are receding faster than light can close the gap. They are slipping away into regions of space that will forever remain beyond our reach. This is not a comfortable thought. There is an entire universe out there, possibly infinite, that we will never see. Galaxies, stars, perhaps civilizations, all existing in a region of space that is causally disconnected from ours. We cannot send signals to them. They cannot send signals to us. The expansion of space has placed them beyond the boundary where communication is possible. They are as unreachable as the past, and yet they are out there right now, existing in the same moment we are, separated from us not by time, but by the geometry of the cosmos itself. For most of human history, we had no idea any of this was true. The universe was thought to be static, unchanging, eternal. Stars and galaxies were fixed in place. The sky looked the same a billion years ago as it does today. Then, in the 1920s, Edwin Hubble, working at the Mount Wilson Observatory in California, made a series of observations that shattered that assumption. He measured the distances to nearby galaxies using a class of pulsating stars called Cepheid variables. Their brightness fluctuates in a way that is directly tied to their true luminosity. Measure the pulse, calculate the brightness, compare it to how bright the star appears from Earth, and you get a distance. Hubble found that the galaxies he was observing were far outside our own Milky Way, millions of light years away. Then he did something even more important. He measured their motion. Light from distant galaxies is redshifted. The wavelengths are stretched, shifted toward the red end of the spectrum. The faster a galaxy is moving away from us, the more its light is redshifted. Hubble found that every galaxy he looked at, with only a few exceptions among the very nearest ones, was redshifted. And the farther away a galaxy was, the faster it was receding. The relationship was linear. Double the distance, double the speed. The universe was not static, it was expanding. And it had been expanding for a very long time. Albert Einstein did not believe it at first. His equations of general relativity, published in 1915, had predicted a dynamic universe, one that either expanded or contracted. Einstein found that result so uncomfortable that he added a term to his equations, the cosmological constant, specifically to force the universe to hold still. When Hubble's observations were published, Einstein reportedly called the cosmological constant his greatest blunder. The universe was expanding, and the math had told him so years before anyone observed it. If the universe is expanding now, it must have been smaller in the past. Run the equations backward and everything converges to a single point. A moment when the density and temperature were infinite, when space and time themselves began, the Big Bang. Not everyone accepted the idea right away. For decades, a rival theory called the steady-state model had its champions. It proposed that the universe had no beginning, that new matter was continuously created to fill the gaps left by expansion, keeping the overall density constant. The debate was fierce. Then, in 1964, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna and kept picking up an annoying hum they could not get rid of. It was faint, uniform, coming from every direction in the sky. They cleaned the antenna. They checked for interference. They even cleared out a nest of pigeons that had been roosting inside the horn. The noise remained. It turned out they had discovered the cosmic microwave background, the afterglow of the Big Bang. The steady-state model collapsed overnight. The universe had a beginning, and we could see the light from it. That discovery changed everything. It gave cosmologists a fixed point in time to work backward from. It confirmed the Big Bang model, and it opened up an entirely new way of studying the universe's structure and evolution. But the CMB, for all its importance, only shows us the universe as it was 380,000 years after the beginning. What happened in between? What happened in the first moments? And what happened after the fog cleared? When did the first stars ignite? When did the first galaxies form? For decades, we could only guess. The universe between 380,000 years and a few 100 million years after the Big Bang was a black box. Astronomers called it the cosmic dark ages. No stars yet, no galaxies, just hydrogen gas slowly clumping together under gravity, waiting for something to light up. Then the James Webb Space Telescope launched in late 2021. Webb was built specifically to see further back in time than any telescope before it. Its 6.5-meter mirror, coated in gold to reflect infrared light, sits in a stable orbit about 1.5 million kilometers from Earth, far beyond the interference of our planet's atmosphere and heat. Infrared is the key. The light from the earliest galaxies has been stretched by the expansion of the universe from visible and ultraviolet wavelengths all the way into the infrared. Hubble, for all its power, could not see far enough into the infrared to catch those signals. Webb can. And almost immediately after it began observing, it started finding galaxies at distances no one had seen before. Galaxies at a redshift of 10, 12, 14, even higher. Galaxies whose light has been traveling toward us for more than 13 billion years. Galaxies we are seeing as they existed when the universe was less than 500 million years old. Some of them are massive, far more massive than the models predicted they should be at that age. They should have been small, dim, struggling to pull themselves together from scattered clouds of gas. Instead, they are bright, structured, filled with hundreds of millions of stars. They look like they have been around for billions of years, but the universe itself was barely a toddler when their light was emitted. Webb did not just push the boundary of the observable universe, it found things on the other side of that boundary that do not fit the script. The first stars, the ones that formed in the cosmic dark ages, have never been directly observed. They are called population 3 stars, and they were giants. Hundreds of times more massive than our sun, burning hydrogen into helium at a ferocious rate, living fast and dying young in spectacular supernova explosions. Those explosions seeded the surrounding gas with the first heavy elements in the history of the universe. Carbon, oxygen, iron, all the ingredients needed for planets and eventually life. From those enriched clouds, the next generation of stars formed, and from those stars, the first galaxies began to assemble. That is the story the models tell. Webb is checking whether the story is true. So far, the answer is complicated. Some of what Webb sees matches the predictions, some of it does not. The galaxies are there, right where they should be in time, but they are bigger, brighter, more organized than anyone expected. That could mean the first stars formed faster than the models allow. It could mean the process of galaxy assembly was more efficient in the early universe. Or it could mean something in our understanding of how stars and galaxies form is incomplete. The tension has not been resolved. The data is still coming in. But one thing is clear, the edge of the observable universe is not empty. It is not quiet. It is crowded with galaxies, blazing with light from an era when the cosmos was just beginning to wake up. And that light has been traveling toward us for more than 13 billion years. Every photon Webb detects from those distant galaxies is a messenger from the past. It carries information about the conditions in the early universe, the temperature, the density, the chemistry. It tells us what the first stars were made of, how fast they were forming, how they died. It is a direct line to a time and place no human will ever visit. The cosmic horizon is not just a limit, it is a window. A way of seeing the universe as it was, layer by layer, era by era, all the way back to the moment the first light broke through the fog. But here is the thing, the horizon is not static, it is moving. As the universe ages, light from more distant regions has time to reach us. The observable universe grows, slowly but measurably. In another billion years, assuming the expansion does not change dramatically, we will be able to see objects that are currently just beyond our reach. Their light will finally arrive. The horizon will shift outward, but at the same time, the acceleration of the universe's expansion is pulling distant galaxies away from us faster and faster. Objects near the edge of the observable universe today will eventually cross a different kind of horizon, the point where the expansion of space between us and them exceeds the speed of light. Once they cross that line, no signal they send will ever reach us. They will fade from view, not because their light is too faint, but because the space between us is growing faster than light can travel through it. The universe will shrink, observationally speaking, even as it continues to expand. We live in a brief window of cosmic time when the universe is old enough for galaxies to have formed, but young enough that we can still see the most distant ones. A few trillion years from now, assuming the acceleration continues, the only galaxies visible from Earth will be the ones gravitationally bound to us, the local group, a small cluster of a few dozen galaxies held together by gravity. Everything else will have been carried beyond the cosmic horizon. The sky will go dark. Future civilizations, if any exist, will look up and see almost nothing. No distant galaxies, no cosmic web, no evidence that the universe extends beyond their local neighborhood. They will have no way of knowing that billions of other galaxies once filled the sky. The evidence will have vanished, redshifted into invisibility, lost to the accelerating expansion of space itself. They will invent their own cosmology, and it will be wrong because the universe will have hidden the truth from them. We are lucky. We live in an era when the universe is still revealing its history, when the light from the edge of everything is still reaching us, when telescopes like Webb can point at a patch of sky no bigger than a grain of sand held at arm's length and find thousands of galaxies, some of them sitting at the very edge of the observable universe, their light stretched and faded, but still carrying the story of where they came from and when they existed. That story is what the next chapter is about. Webb was built to do one thing better than any telescope in history: see backward in time, not metaphorically, not in some poetic sense. Actually see the light from objects so distant that what we are observing is the universe as it existed billions of years before Earth, before the Sun, before the Milky Way had finished pulling itself together. The James Webb Space Telescope was engineered from the ground up to look at the earliest galaxies that ever formed, to catch photons that have been traveling through expanding space for more than 13 billion years, and to decode what those photons can tell us about how everything began. It launched on Christmas Day, 2021, folded up inside the nose cone of an Ariane 5 rocket, and spent the next month unfolding itself in space like some impossibly delicate piece of origami. The sunshield alone, 5 layers of material thinner than a human hair, stretched out to the size of a tennis court. The mirror, 18 hexagonal segments coated in gold, opened like a flower. By late January 2022, Webb had reached its destination, a gravitationally stable point called L2, about 1.5 million kilometers from Earth, where the Sun and Earth's gravity balance out. It sits there now, staring into the dark, collecting light that left its source when the universe was an infant. The gold coating is not decorative. Gold reflects infrared light better than almost anything else, and infrared is the entire reason Webb exists. Visible light, the narrow slice of the spectrum our eyes can see, is useless for observing the most distant objects in the universe. By the time their light reaches us, it has been stretched by the expansion of space so severely that it arrives in wavelengths far redder than our eyes can detect. Ultraviolet light emitted by young hot stars in a galaxy 13 billion light-years away gets pulled and pulled and pulled by the stretching of space until it shifts through visible red, past the edge of what we can see, and into the infrared. Hubble, for all its power, was built primarily for visible and ultraviolet light. It could peek into the near-infrared, but only weakly. Webb was built to live there. Every instrument aboard is tuned to capture infrared photons, and the telescope itself operates at temperatures cold enough to keep its own heat from drowning out the faint signals it is trying to detect. This is why Webb can see what Hubble could not. It is not just that Webb's mirror is bigger, though it is. It is not just that Webb is more sensitive, though it is. It is that Webb is looking in the right part of the spectrum, the part where the earliest galaxies are actually visible. Hubble strained to see galaxies at a redshift of about 11, which corresponds to light emitted roughly 400 million years after the Big Bang. Webb routinely finds galaxies at redshifts of 12, 13, 14 and higher. In its first year of operations alone, Webb discovered dozens of galaxies that are older, more distant, and stranger than anything Hubble ever found. Redshift, if the term means nothing to you, is just a way of measuring how much the light from an object has been stretched. The higher the redshift number, the farther away the object is, and the longer its light has been traveling. A redshift of 1 means the light has been stretched to about twice its original wavelength. A redshift of 10 means it has been stretched to about 11 times its original wavelength. A redshift of 14, which Webb has now detected in multiple galaxies, means the light has been stretched by a factor of 15. The universe was less than 300 million years old when that light was emitted. These are not galaxies caught in their middle age. These are galaxies caught in the act of being born. One of the first deep images Webb produced, released in July 2022, was called the First Deep Field. It was a tiny patch of sky, a region so small that if you held a grain of sand at arm's length, it would cover the entire area Webb was looking at. The telescope stared at that patch for more than 12 hours, collecting every photon it could. When the image was processed, it contained thousands of galaxies. Some of them were relatively nearby, cosmically speaking. Others were so distant their light had been traveling for more than 13 billion years, and scattered throughout the image were objects that should not have been there. Galaxies that were too bright, too massive, too well organized for the age they appeared to be. The expectation, based on decades of modeling, was that the first galaxies would be small, chaotic, barely held together. Star formation in the early universe was supposed to be slow and inefficient. The gas clouds had no heavy elements yet, no carbon or oxygen or iron to help them cool and collapse. The first stars, called population 3 stars, were predicted to be enormous, hundreds of times the mass of the Sun, burning through their fuel in just a few million years and exploding as supernova. Those explosions would scatter the first heavy elements into space, seeding the next generation of stars. Galaxies would assemble gradually, piece by piece, over hundreds of millions of years. That was the script. Webb found galaxies that looked like they had skipped the first act entirely. Take J's GSZ 13-0, one of the earliest confirmed galaxies Webb has observed. It sits at a redshift of 13.2. The light we are seeing left that galaxy when the universe was about 330 million years old. That is early, extremely early. And yet, the galaxy is not a scattered mess of gas and a handful of stars struggling to ignite. It contains hundreds of millions of stars. It has structure. It is bright enough to be detected across more than 13 billion light-years of space. To build a galaxy like that in 330 million years, stars would have had to form at a rate far faster than current models predict. The gas would have had to collapse into stars with almost perfect efficiency. And yet there it is, fully formed, shining back at us from the edge of time. Or consider Sears 93316, Another early candidate initially thought to sit at a redshift of 16.7. If that measurement had held, it would have placed the galaxy just 250 million years after the Big Bang, pushing right up against the boundary of when the first stars should have even been possible. Follow-up observations revised the redshift downward, but the galaxy is still older and more massive than the models comfortably allow. And it is not alone. Webb has found a growing list of these objects. Galaxies at redshifts of 12, 13, 14, all of them brighter and more mature than they should be. This is not a small problem. If galaxies could form this quickly in the early universe, then something in our understanding of star formation is wrong. Either the first stars were far more efficient at converting gas into starlight than we thought, or the conditions in the early universe allowed for a kind of accelerated assembly that we have no real analog for in the present day. Some astronomers have proposed that the first molecular clouds collapsed and ignited stars at rates 10 or 20 times faster than what we see in modern galaxies. Others suggest that supermassive black holes, which we know existed in the early universe, may have played a role in jump-starting galaxy formation by heating and compressing the surrounding gas. The black hole explanation is worth pausing on because Webb has found evidence of that too. Several of the earliest galaxies Webb has observed show signs of hosting active supermassive black holes at their centers, black holes weighing millions or even billions of times the mass of the Sun. That alone is a problem because black holes are supposed to grow slowly. A black hole forms when a massive star collapses. It starts out weighing maybe 10 or 20 times the mass of the Sun. From there, it grows by accreting gas or merging with other black holes. Both processes take time. To grow a billion solar mass black hole starting from a stellar seed, you need hundreds of millions of years at minimum, even if the black hole is feeding at the maximum possible rate. The black holes Webb is finding in the early universe do not have that kind of time. The universe itself is only a few 100 million years old when we are seeing them. Either they grew impossibly fast, or they did not start as stellar mass seeds at all. Enter the idea of direct collapse black holes. In this scenario, a giant cloud of primordial gas, a cloud weighing tens or hundreds of thousands of solar masses, skips the star formation phase entirely and collapses straight into a black hole. No star, no supernova, just a sudden gravitational collapse triggered by the sheer weight of the gas itself. If that process happened in the early universe, it would give you black holes that start out already weighing 100,000 solar masses or more. From there, growing to a billion solar masses in a few 100 million years becomes a lot more plausible. The problem is, we have never observed a direct collapse black hole forming. We do not know for certain that they can happen. But Webb is finding black holes that are hard to explain any other way. One of the most surprising discoveries came from an object called GNZ11, a galaxy sitting at a redshift of about 11. For years, it held the record as the most distant galaxy ever observed, first spotted by Hubble and then studied in detail by Webb. The galaxy is extremely luminous, far brighter than it should be for its size, and Webb's spectroscopy revealed something strange. The light from the galaxy shows the signature of a supermassive black hole at its center, actively feeding on surrounding gas. The black hole is estimated to weigh about 1 million solar masses. That might not sound enormous compared to the supermassive black holes at the centers of modern galaxies, some of which weigh billions of solar masses. But this black hole exists when the universe is only 400 million years old. Growing something that heavy in that amount of time pushes right up against the limits of what accretion physics allows. And the galaxy itself, bright as it is, seems to be glowing not just from stars, but from the black hole's feeding activity. The gas spiraling into the black hole is heated to millions of degrees, releasing enormous amounts of energy, enough to outshine entire populations of stars. If a significant fraction of the early galaxies Webb is finding are powered by black holes rather than stars, it changes the entire picture of what the early universe looked like. It means the first light in the cosmos may not have come from stars at all. It may have come from monsters, from black holes gorging themselves on primordial gas, blazing so brightly that they look like galaxies from a distance. And if that is true, then the timeline for how structure formed in the universe needs to be rewritten. The cosmic dark ages, the period between when the cosmic microwave background was emitted and when the first stars lit up, lasted somewhere between 100 and 200 million years. During that time, the universe was filled with neutral hydrogen gas, slowly clumping together under gravity, but not yet hot enough or dense enough to ignite. It was a period of absolute darkness. No stars, no galaxies, no light sources of any kind. Then something happened. The first stars formed, or the first black holes collapsed, and they began emitting ultraviolet radiation powerful enough to ionize the surrounding hydrogen. This process, called reionization, spread outward in bubbles around the first light sources, gradually clearing the fog of neutral hydrogen and making the universe transparent to light. By the time the universe was about 1 billion years old, reionization was complete. The dark ages were over. The universe was filled with light. Webb is giving us our first direct look at the tail end of that process. Some of the galaxies it has found sit right at the boundary between the dark ages and the era of reionization. Their light shows the signature of hot young stars blasting out ultraviolet photons, carving out bubbles of ionized gas in the surrounding fog. Other galaxies show no such signature, which might mean they existed just before reionization reached them, still surrounded by neutral hydrogen, still living in the dark. By mapping these galaxies, their distances, their brightness, their spectra, astronomers are reconstructing the timeline of when and how the universe lit up, and so far the picture is messier and more complicated than the models predicted. One of the tools Webb uses to study these distant galaxies is called spectroscopy. Instead of just taking a picture, Webb splits the incoming light into its component wavelengths, producing a spectrum. That spectrum is like a fingerprint. It tells you what the light is made of. If the galaxy contains oxygen, you see a specific set of dark or bright lines in the spectrum where oxygen atoms absorb or emit light. If it contains carbon, you see different lines. If it contains hydrogen, which every galaxy does, you see the characteristic signature of hydrogen emission. By analyzing those lines, astronomers can determine the chemical composition of the galaxy, how fast it is forming stars, whether it contains a black hole, and how far away it is. The redshift is measured directly from the spectrum by comparing where the lines appear to where they should appear if the galaxy were sitting still. In several of the earliest galaxies Webb has studied, the spectra show something unexpected: oxygen. That single element changes the conversation because oxygen is not primordial. It cannot exist in significant amounts without stars first being born, living their lives, fusing lighter elements into heavier ones in their cores, and then dying in supernovae that scatter those heavier elements into space. Every oxygen atom in the universe was forged inside a star. So when Webb detects oxygen in a galaxy that existed only 300 million years after the Big Bang, it means stars had already been born, lived and died inside that galaxy, all within a window of time that should not have been long enough for any of that to happen. The first stars are supposed to live for a few million years before exploding. The debris from those explosions has to cool and collapse into new stars. That cycle has to repeat multiple times before you build up enough oxygen to show up in a spectrum. And all of that has to happen in less than 300 million years. The math is tight, uncomfortably tight. Some researchers have suggested that the first stars were not just massive, but ferociously efficient, that they formed in enormous numbers all at once, lived fast, died young, and seeded the surrounding gas with heavy elements at a rate far faster than anything we see in the modern universe. If that is true, the first few 100 million years of cosmic history were a wildfire of star formation, a brief chaotic period when the rules were different. Others have proposed that the metallicity, the fraction of heavy elements in these early galaxies, is being overestimated, that the oxygen signatures are coming from a small number of very hot stars rather than a large population of older ones. The debate is ongoing. The data is still being analyzed, but the tension is real. Then there is the dust. Dust, in astronomical terms, just means tiny solid particles floating in space, mostly carbon and silicates. Dust is important because it absorbs and scatters light, particularly ultraviolet and visible light, and re-emits that energy in the infrared. Hubble, which observes primarily invisible light, struggles to see through dust. Entire regions of star formation in nearby galaxies are completely obscured to Hubble because the dust is so thick. Webb, observing in the infrared, can see right through it. The dust does not block infrared light the way it blocks visible light. It just glows faintly in the infrared from the heat of nearby stars. Webb has found dust in some of the earliest galaxies it has observed. That is strange because dust is made of heavy elements: carbon, oxygen, silicon, iron, elements that do not exist until stars have lived and died. The presence of dust in galaxies only a few 100 million years old implies that not only had stars already formed and exploded, but the debris from those explosions had time to condense into solid grains and spread throughout the galaxy. That is another step in the process, another thing that takes time, and the clock keeps getting tighter. One particularly striking example comes from a galaxy called a 2744 YD4, observed by Webb in a region of sky behind a massive galaxy cluster. The cluster acts as a gravitational lens, bending and magnifying the light from more distant objects behind it. A 2744 YD4 sits at a redshift of about 8.4, making it one of the more distant galaxies Webb has studied in detail. And its spectrum shows a significant amount of dust. Enough dust that astronomers estimate the galaxy must have already gone through multiple generations of star formation. Stars formed, exploded, seeded the gas with heavy elements, and then new stars formed from that enriched gas. All of this happened when the universe was less than 600 million years old. The galaxy is not a newborn, it is already mature, and that raises the same uncomfortable question: how did this happen so fast? The answer, if there is one, probably involves a combination of factors. The early universe was denser. The gas clouds were closer together, making collisions and mergers more common. The first stars may have been more massive and shorter-lived than stars today, cycling through their lifespans faster and enriching the gas more quickly. Supermassive black holes may have played a role in compressing and heating the gas, triggering bursts of star formation. Or there may be something about the physics of the early universe that we simply do not understand yet. Some process or feedback loop that we have not accounted for in the models. What is clear is that the standard picture of galaxy formation, the one that has guided cosmology for decades, is under pressure. Webb is finding galaxies that are too big, too bright, too mature for the ages we are seeing them at. And the more Webb looks, the more of these objects it finds. They are not rare outliers, they are common. A significant fraction of the galaxies Webb observes in the early universe show these characteristics. Either the models are wrong, or the early universe was fundamentally different from what we assumed. Both possibilities are unsettling, and yet the models are not being thrown out. Not yet. Science does not work that way. When observations conflict with predictions, the first step is to check the observations. Are the distances correct? Are the redshifts reliable? Could there be contamination in the spectra, some other source of light mimicking the signature of a distant galaxy? Webb's team has been careful. Every high redshift galaxy candidate gets follow-up spectroscopy to confirm the distance. The redshifts are measured multiple times using different instruments. The contamination scenarios have been modeled and ruled out in most cases. The observations are solid. The galaxies are real. The distances are real. The tension is real. So the next step is to adjust the models. Maybe the star formation efficiency in the early universe was higher than current simulations assume. Maybe the initial mass function, the distribution of stellar masses at birth, was skewed toward heavier stars in the first generation. Maybe feedback from supernova and black holes was less effective at shutting down star formation than we thought. Researchers are running new simulations, tweaking the parameters, trying to find a combination of conditions that can reproduce what Webb is seeing. Some of those models are starting to get close, but they require assumptions that push the boundaries of what we consider plausible. High star formation rates, low feedback efficiency, rapid black hole growth, all of it happening faster than the present-day universe allows. The cosmic dark ages are not dark anymore. Webb is lighting them up, galaxy by galaxy, spectrum by spectrum, and what is being revealed is a universe that wasted no time getting started. The first few 100 million years were not a slow, quiet build-up. They were an explosion of activity, a frenzy of star formation and black hole growth that built massive structures in a fraction of the time it should have taken. Whether the models catch up remains to be seen, but the data is here, the light has arrived, and it is telling a story that no one predicted. The discoveries are not slowing down. Webb is still in its early years of operation. The telescope was designed to last at least 10 years, possibly longer. Every observation adds new galaxies to the catalogue, new spectra to analyze, new puzzles to solve. And beyond Webb, the next generation of telescopes is already being planned. Ground-based observatories with mirrors 30 meters across. Space telescopes optimized for even longer infrared wavelengths. Instruments capable of detecting the faint signatures of individual stars in the earliest galaxies, or the emission lines from molecules in the atmospheres of planets orbiting distant suns. The edge of the observable universe is being mapped in greater detail every year, and the map keeps getting stranger. But Webb is not working alone. Hubble is still operational, still collecting data, still contributing observations that complement what Webb sees. Together, the two telescopes cover a wide range of wavelengths, from ultraviolet through visible into the infrared. Where Hubble sees young blue stars, Webb sees the dust and gas surrounding them. Where Hubble hits a wall at redshift 11, Webb keeps going, pushing deeper into the past. And in a few years, the two will be joined by new missions. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will have a field of view 100 times larger than Hubble or Webb, allowing it to survey vast swaths of the sky and find rare distant objects that single pointings would miss. The European Space Agency's Euclid mission is already in orbit, mapping the distribution of galaxies across billions of light-years to study the nature of dark energy. The data from all these missions will feed into the same models, the same simulations, the same effort to understand how the universe went from a hot, dense fog to the vast, structured cosmos we see today. The infant universe is no longer a mystery we can only guess at. It is a place we can observe directly, a time we can study in detail. And what we are finding is not the slow, patient assembly of structure that the textbooks described. It is fast, chaotic, efficient, and strange. Webb is giving us the first clear look at that era, and the picture it is revealing will keep astronomers busy for decades. Webb is peeling back the first few 100 million years of cosmic history, finding galaxies that should not exist yet, black holes that grew too fast, stars that lit up too early. That story is still being written. The data is still coming in. But before Webb, before we had the sharpest infrared eye ever pointed at the sky, there was another telescope that changed everything. And it did not do it by looking at something dramatic. It did it by staring at nothing. In December 1995, the Hubble Space Telescope aimed its mirror at one of the emptiest patches of sky anyone could find, a tiny region in the constellation Ursa Major near the handle of the Big Dipper, where ground-based surveys had found essentially nothing, no bright stars, no nearby galaxies, no obvious targets of interest, just dark, empty space. The kind of spot most astronomers would ignore completely because there was nothing there worth looking at. Robert Williams, the director of the Space Telescope Science Institute at the time, decided to point Hubble at it anyway. Not for a few minutes, not for a few hours, for 10 straight days. The observation was controversial. Hubble time is expensive. Every minute the telescope spends staring at one target is a minute it is not spending on something else. Astronomers from around the world submit proposals every year competing for time on Hubble, and only a fraction of those proposals get approved. The idea of burning 10 consecutive days on a blank piece of sky with no guarantee of finding anything struck many people as a waste. Williams had the authority to allocate a portion of Hubble's schedule as director's discretionary time, and he used it. He wanted to know what was out there in the dark, whether the universe, when you stared long enough at a spot that looked empty, would reveal something no one expected. It did. When the exposures were combined and the image was processed, that empty patch of sky contained more than 3,000 galaxies, not stars, galaxies, entire collections of billions of stars, scattered across the frame like grains of sand on a beach. Some of them were relatively nearby, bright and well-defined, their spiral arms clearly visible. Others were faint smudges, so distant their light had been traveling for billions of years before it reached Hubble's mirror. The image covered an area of sky roughly 1/24 millionth of the total celestial sphere. To put that in a more tangible way, if you held a grain of sand at arm's length and looked at the sky through the tiny patch that grain covered, you would be looking at an area about the size of the Hubble Deep Field, and in that grain-sized patch there were more than 3,000 galaxies. The statistical implication was immediate and overwhelming. If one tiny random patch of empty sky contained 3,000 galaxies, then the entire sky must contain billions, possibly hundreds of billions. The universe was far more crowded than anyone had fully appreciated. Every direction you looked, if you looked long enough, revealed galaxies stretching back through time. The apparent emptiness of the night sky was an illusion caused by the faintness of distant objects and the limits of human vision. Point a sensitive enough telescope at any spot, and the darkness fills with light. The Hubble Deep Field became one of the most famous images in astronomy. It was not the prettiest picture Hubble ever took. It did not show a colorful nebula, or a dramatic supernova, or a perfectly symmetrical spiral galaxy. It showed a field of tiny dots and smudges, most of them so faint they were barely distinguishable from noise. But the scientific impact was enormous. For the first time, astronomers had a direct observational census of galaxies across a huge range of distances, all in one image. They could see galaxies as they appeared 1 billion years ago, 2 billion years ago, 5 billion years ago, all the way back to galaxies whose light had been traveling for more than 10 billion years. The image was a timeline of galaxy evolution laid out in a single frame. And the story that timeline told was surprising. The galaxies in the deep field did not all look the same. The nearby ones, the ones whose light had only been traveling for a few billion years, were mostly well-organized spirals and ellipticals, the kind of galaxies astronomers were used to seeing. The distant ones, the ones seen as they existed 10 or 11 billion years ago, looked different. Smaller, more irregular, often distorted or clumpy. They looked like galaxies still in the process of assembling, colliding and merging, forming stars in chaotic bursts, rather than the steady measured pace seen in modern galaxies. The deep field provided direct visual evidence for something theorists had long suspected. Galaxies evolve. They start out small and messy, grow through mergers and accretion, and over billions of years settle into the smooth, structured forms we see in the nearby universe today. The Hubble Deep Field was so successful that Hubble did it again. In 2003 and 2004, the telescope spent nearly 4 months staring at an even smaller patch of sky in the constellation Fornax, collecting more than 11 days of total exposure time. The result was the Hubble Ultra Deep Field, and it pushed deeper than the original. Where the deep field had found galaxies out about 12 billion light-years, the Ultra Deep Field found galaxies at 13 billion light-years, galaxies whose light had been traveling since the universe was less than 1 billion years old. The image contained roughly 10,000 galaxies in an area of sky about 1/10 the size of the original deep field. 10,000 galaxies in a region you could cover with a pinhead held at arm's length. Then, in 2012, Hubble pushed even further. By reprocessing the ultra-deep field data and adding new exposures, astronomers created the Extreme Deep Field, the XDF. This version reached back to galaxies seen as they existed just 450 million years after the Big Bang. The faintest galaxies in the XDF are about 10 billion times dimmer than the faintest stars visible to the naked eye. Detecting them required Hubble to collect photons over hundreds of hours, adding up every tiny trickle of light until the signal rose above the noise. And even then, many of those galaxies are just barely visible, a handful of pixels on the detector, a faint red smudge that could easily be mistaken for noise if you did not know what you were looking at. This is where the concept of look-back time becomes critical. Every object in the sky is not just far away in space, it is far away in time. Light does not travel instantaneously. It moves at 300,000 kilometers per second, which is fast by human standards but slow on cosmic scales. The light from the sun takes about 8 minutes to reach Earth. If the sun vanished right now, we would not know for 8 minutes because the last light it emitted would still be traveling toward us. The light from the nearest star beyond the sun, Proxima Centauri, takes about 4 years to reach us. When we look at Proxima Centauri, we are not seeing it as it is today. We are seeing it as it was 4 years ago. Look at a galaxy 1 billion light-years away, and you are seeing it as it was 1 billion years ago. The farther you look, the further back in time you see. The Hubble Deep Fields are not maps of where galaxies are today. They are maps of where galaxies were billions of years ago. The light from those galaxies has been traveling toward us for most of the age of the universe, and in that time, the universe has changed. The galaxies have aged. Many of them have merged with other galaxies. The stars inside them have lived and died. The gas clouds have been enriched with heavy elements from generations of supernova. If you could somehow see those same galaxies as they exist today, they would look completely different, older, larger, possibly unrecognizable. But we cannot see them as they are today. We can only see them as they were when their light was emitted. The universe has a built-in delay. The deeper we look into space, the further we look into the past. And there is another twist. The distances we measure are not the distances objects actually are from us right now. They are the distances the light has traveled, and because space itself has been expanding the entire time that light was in transit, the objects have been carried further away. A galaxy whose light has been traveling for 13 billion years is not 13 billion light-years away today. It is much farther. The expansion of space has been pulling it away from us the entire time its light was traveling toward us. Run the math, and that galaxy is currently sitting about 46 billion light-years away, even though its light only traveled for 13 billion years. The universe is older than 13.8 billion years. Space has been stretching, and the edge of the observable universe, the farthest distance from which light has had time to reach us, sits at about 46 billion light-years in every direction. The observable universe is a sphere roughly 93 billion light-years across. That number confuses people. How can the universe be 93 billion light-years across if it is only 13.8 billion years old? The answer is expansion. Space does not sit still. It has been growing since the Big Bang, and it has been growing faster than light can cross it. Objects near the edge of the observable universe are receding from us faster than light. That does not violate relativity, because the objects themselves are not moving through space faster than light. Space itself is expanding, carrying them along. And once an object crosses a certain threshold, the expansion of space between us and it exceeds the speed of light permanently. No signal it sends will ever reach us. The light will be emitted, but the space between us will grow faster than the light can cross it. The object slips beyond the cosmic horizon, and from our perspective it vanishes. This is happening right now. Galaxies at the edge of the observable universe are slipping away. In a few billion years, some of the galaxies we can see today will have crossed that threshold. Their light will still be reaching us for a while, redshifted and fading, but eventually even that will stop. The universe will have carried them beyond the point where their light can ever catch up to us. The observable universe will shrink, even though the actual universe continues to expand. Future astronomers, assuming anyone is still around to do astronomy trillions of years from now, will look up and see almost nothing. The only galaxies visible will be the ones gravitationally bound to our local neighborhood, the few dozen galaxies in the local group that are close enough that gravity holds them together despite the expansion of space. Everything else will have been carried beyond the horizon. The sky will go dark, and those future astronomers will have no way of knowing that billions of galaxies once filled the sky. The evidence will have vanished. The universe will have hidden its own history. We live in a lucky era. The universe is old enough that galaxies have formed and matured, but young enough that we can still see the most distant ones. Hubble's deep fields captured that moment. They showed us a universe filled with galaxies at every distance, every age, every stage of evolution. From the nearby well-organized spirals a few billion light-years away, to the faint, irregular clumps more than 13 billion light-years distant, the deep fields are a visual history of how structure formed in the cosmos. And the sheer number of galaxies in those images drives home just how vast and crowded the universe actually is. 10,000 galaxies in an area the size of a pinhead. That is the number astronomers kept coming back to because it makes the scale tangible. Hold a pin at arm's length and look at the sky through the tiny patch of darkness the head covers. In that patch, if you could see far enough, there are 10,000 galaxies, each one containing billions of stars, each one stretching across tens or hundreds of thousands of light years. Each one home to gas clouds, dust lanes, possibly planets, possibly life. And that is just one tiny patch. The entire sky contains tens of billions of similar patches. Multiply it out, and the numbers become absurd. Hundreds of billions of galaxies in the observable universe, possibly more. Each one a universe unto itself. The deep fields also revealed something unsettling. The faintest galaxies in the images, the ones at the very edge of Hubble's detection limit, are so faint and so distant that we are seeing them right at the boundary of the observable universe. Their light has been traveling for more than 13 billion years. They exist in an era when the universe was less than 1 billion years old, and many of them are small, faint, irregular. They are the building blocks of larger galaxies, the seeds that will merge and grow over billions of years to form the massive galaxies we see in the nearby universe. Some of those seeds may have merged to form the Milky Way. The stars in our own galaxy, the Sun included, may have formed from gas that was once part of a small irregular galaxy like the ones in the ultra-deep field. We are looking at our own distant ancestors, scattered across the frame, too far away and too faint to ever visit, but close enough in the record of light that we can see what they looked like. And we are looking at galaxies that no longer exist, at least not in the form we are seeing them. A galaxy whose light has been traveling for 13 billion years has had 13 billion years to change. It has formed new stars, lost old ones to supernova, possibly collided with another galaxy and merged into something larger. The image we are seeing is a fossil, a snapshot of something that existed once but has since evolved into something else. The universe is full of fossils like this. Every distant object we observe is a relic of a time that no longer exists. Astronomy is a form of time travel, but only in one direction. We can look into the past as deeply as our instruments allow. We can see the universe as it was billions of years ago, but we can never see it as it is right now. By the time the light from a distant galaxy reaches us, the galaxy has already moved on. Hubble's deep fields were groundbreaking when they were released, and they remain some of the most scientifically valuable images ever taken. But Hubble was not built for the deepest observations. It was built for visible and ultraviolet light with limited sensitivity in the infrared. That meant it could see galaxies out to about 13 billion light years, but beyond that, the light was stretched so far into the infrared that Hubble's instruments could barely detect it. Hubble was bumping up against a wall, not because its mirror was too small or its instruments were not sensitive enough, but because it was looking in the wrong part of the spectrum. The earliest galaxies, the ones forming in the first few 100 million years after the Big Bang, emit most of their light in wavelengths that Hubble simply cannot see. That is where Webb comes in, and that is why Webb has been able to push further into the past than Hubble ever could. But Hubble paved the way. It proved that staring at nothing long enough would reveal something extraordinary. It showed that the universe is far stranger and more crowded than the night sky suggests. And it gave astronomers the first clear timeline of galaxy evolution, stretching from the nearby universe all the way back to the edge of time. There is one more detail worth mentioning. The galaxies in the deep fields are not evenly distributed. They cluster. Some regions of the image are packed with galaxies, while others are relatively empty. That clustering is not random. It reflects the underlying structure of the universe, the cosmic web of filaments and voids that has been growing since the earliest moments after the Big Bang. Gravity pulls matter together into clumps. Those clumps attract more matter. Over time, the clumps grow into galaxies, and the galaxies pull together into clusters, and the clusters form superclusters connected by long filaments of gas and dark matter. The voids, the empty regions, are not truly empty. They contain gas and dark matter, just much less of it, and they grow over time as matter flows out of them and into the denser regions. The deep fields capture a slice of that structure. The clustering pattern visible in the images matches the predictions from simulations of cosmic structure formation almost perfectly. The universe is behaving the way the models say it should, at least on large scales. On smaller scales, though, things get messier. Individual galaxies do not always follow the script. Some of the galaxies in the ultra-deep field are larger than they should be for their age. Some are forming stars faster than the models predict. Some show signs of recent mergers or interactions with other galaxies. The average behavior matches the models, but the individual cases are full of surprises. That is what makes the deep field so valuable. They are not just pretty pictures, they are data. Every galaxy in the frame is a data point. Every color, every shape, every brightness measurement is a clue about how that galaxy formed, how old it is, how fast it is forming stars, how much gas and dust it contains. Multiply that by 10,000 galaxies and you have a dataset rich enough to test and refine the models of galaxy formation in ways that were not possible before. Astronomers have spent years analyzing the deep fields, measuring the properties of individual galaxies, tracking how those properties change with distance and time, building up a statistical picture of how galaxies evolve, and the picture that has emerged is one of constant change. Galaxies in the early universe are smaller, bluer, more gas-rich, forming stars at higher rates. Galaxies in the nearby universe are larger, redder, more gas-poor, forming stars more slowly. The transition happens gradually over billions of years. Star formation peaks around 10 billion years ago, when the universe is about a third of its current age, and then declines. Today, most galaxies are no longer forming stars at high rates. They have used up most of their gas, or the gas has been heated and blown out by supernova and black hole activity. The universe is aging. The era of rapid galaxy growth is over. We live in a quieter, more settled cosmos. But even in the nearby universe, there are exceptions. Galaxies that are still forming stars at high rates, still growing, still actively evolving. The Hubble deep fields contain examples of those too. Spiral galaxies with bright blue arms where new stars are being born. Irregular galaxies distorted by recent mergers. Galaxies with active supermassive black holes at their centers, feeding on gas and lighting up their surroundings. The universe is not static. It is still changing, just more slowly than it did billions of years ago. And the deep fields give us a front-row seat to that change, capturing galaxies at every stage of their life cycle in a single image. The legacy of the Hubble deep fields is not just the images themselves. It is the way those images changed how astronomers think about the universe. Before the deep fields, galaxy surveys were limited to relatively nearby objects. The faintest galaxies visible in ground-based telescopes were typically no more than a few billion light-years away. The deep fields extended that reach by an order of magnitude, revealing galaxies 10 or 12 or 13 billion light-years distant. That leap backward in time opened up an entirely new era of cosmic history for study. It showed that the early universe was not some abstract theoretical construct. It was a real place, full of real galaxies, and we could see it directly by pointing a telescope at it and waiting long enough for the light to add up. And the technique worked. The deep field method, staring at a single patch of sky for days or weeks to collect faint light, has been used repeatedly since the original Hubble deep field. Hubble itself has done multiple deep fields in different parts of the sky. The Chandra X Ray Observatory has done deep fields in X-rays, revealing distant black holes and galaxy clusters. The Spitzer Space Telescope, which observed in the infrared before Webb, did its own deep fields and found dusty galaxies hidden from Hubble's view. And now Webb is doing deep fields in the near and mid-infrared, pushing even deeper than Hubble ever could. The technique has become a standard tool in observational cosmology. If you want to study the distant universe, you point your best telescope at a piece of empty sky and you wait. The results are always surprising. Every deep field reveals galaxies that were not expected, objects that do not quite fit the models, phenomena that raise new questions. The universe refuses to be simple. It keeps throwing curveballs, and that is what makes it worth studying. If the deep fields had shown exactly what the models predicted, they would have been less interesting. The fact that they keep finding things that do not quite fit is what drives the field forward. It forces astronomers to refine their models, to account for processes they had overlooked, to test new ideas about how galaxies form and evolve. The deep fields are not just windows into the past, they are tests of our understanding. And so far, the universe is passing some parts of the test and failing others. But the deep fields are limited. They cover tiny regions of sky. The XDF, for all its depth, covers an area smaller than a pinhead held at arm's length. That is enough to give a statistical sense of how many galaxies are out there, but it is not enough to capture the full diversity of the universe. There are rare objects, unusual galaxies, one-off events that only happen in a small fraction of the sky. To find those, you need wider surveys that cover larger areas, even if they do not go as deep. And that is where the next generation of telescopes comes in. Webb, with its infrared sensitivity, can go deeper than Hubble, but its field of view is smaller. The Nancy Grace Roman Space Telescope, set to launch in the next few years, will have a field of view 100 times larger than Hubble or Webb. It will be able to survey huge swaths of sky, finding rare distant objects that would never show up in a deep field simply because the deep field was not looking in the right place. Together, these telescopes will fill in the gaps, mapping the universe at every scale from the tiniest deep field to the widest surveys. And all of it starts with the realization that the night sky is not empty, that a grain of sand held at arm's length covers a patch of sky containing 10,000 galaxies, that every direction you look, if you look deeply enough, reveals a universe filled with structure and history stretching back to the beginning of time. The Hubble deep fields made that tangible. They took an abstract idea, the vastness of the universe, and turned it into something you could see. A single image containing thousands of galaxies, each one a world unto itself, each one billions of light years away, each one visible only because its light has been traveling toward us for most of the age of the cosmos. But the cosmos is bigger than galaxies, bigger than the observable universe. There are frontiers much closer to home that are just as strange and just as poorly understood, places we can actually visit if we build the right spacecraft, objects at the edge of our own solar system, drifting in the cold and the dark, waiting to be explored. Here is the shift you were not expecting. After staring at galaxies 46 billion light-years away, after counting 10,000 of them in a patch of sky the size of a pinhead, after watching Webb pull back the curtain on the first few 100 million years of cosmic history, we are going to turn around and look at something close. Not close in the way the moon is close. Close in the way the far edge of your own backyard is close compared to the other side of the planet. We are going to talk about the outer solar system, the frozen frontier sitting just a few billion miles from the sun. The place where sunlight fades to almost nothing, where temperatures drop to a handful of degrees above absolute zero, and where icy worlds drift in the dark like forgotten relics of the time our solar system was born. This is not interstellar space yet, but it is the doorstep, the place where the sun's influence begins to fade and the true emptiness of the void starts to take over. Most people think the solar system ends at Neptune, or maybe Pluto, if they remember that Pluto exists. That makes sense. Neptune is the 8th planet, orbiting about 30 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. 30 times that is about 2.8 billion miles. Pluto swings out as far as 50 astronomical units at the farthest point in its orbit. That is 4.6 billion miles. And for a long time, that was the edge. Beyond Pluto, there was nothing. Just empty space stretching out to the nearest stars, a gulf so vast that even light takes more than 4 years to cross it. Except there is not nothing. There is a lot of something. An entire population of icy bodies, dwarf planets, comet nuclei, chunks of rock and frozen methane and water ice, all drifting in the cold outer reaches of the solar system. Some of them are hundreds of miles across, some are a few feet. Some are bright enough to be detected from Earth with a decent telescope. Others are so dark and so distant that we have only found them in the last 20 years, and we are still cataloging new ones every year. This region, stretching from just beyond Neptune out to distances 50 or 60 or even 100 times farther from the Sun than Earth is, has a name, the Kuiper Belt. And it is full. The Kuiper Belt was predicted before it was discovered. In 1951, a Dutch astronomer named Gerard Kuiper proposed that the solar system did not just end abruptly at Neptune. There should be a reservoir of icy debris left over from the formation of the planets, sitting in a broad ring beyond the orbit of the outermost planet. Comets, the ones that swing into the inner solar system every few decades or centuries, have to come from somewhere. They cannot last forever. Every time a comet passes near the Sun, it loses material. The ice sublimates, the dust boils off, and the comet gets smaller. After a few hundred passes, there is nothing left. If comets have been visiting the inner solar system for billions of years, and they only last a few hundred orbits, then there must be a source constantly replenishing them. Kuiper suggested the source was a belt of icy objects beyond Neptune. He was right. The first Kuiper Belt object after Pluto was discovered in 1992 by David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii. They had been searching for years, taking long exposures of the outer solar system, looking for faint, slowly moving objects that were too far away and too dim for earlier surveys to catch. They found one, a small icy body orbiting about 42 astronomical units from the Sun. They designated it 1992 QB1, and it was proof that Pluto was not alone. Since then, astronomers have found more than 2,000 Kuiper Belt objects, and estimates suggest there are tens of thousands of them larger than 60 miles across, with millions of smaller ones mixed in. The Kuiper Belt is not empty space, it is a graveyard. A frozen archive of material left over from the time the planets were forming 4.5 billion years ago. Pluto is the most famous resident, not because it is the largest, though for a long time we thought it was, and not because it is the most interesting, though it turned out to be far stranger than anyone expected. Pluto is famous because it was discovered first in 1930 by Clyde Tombaugh at Lowell Observatory in Arizona. For 76 years, Pluto was classified as the 9th planet. Then in 2005, astronomers discovered Eris, another icy body in the Kuiper Belt, slightly more massive than Pluto, but much farther away, orbiting at about 96 astronomical units. That discovery forced a question. If Eris was bigger than Pluto, should it be called a planet too? And if so, what about all the other large Kuiper Belt objects that were being found at a steady pace? Where do you draw the line? The International Astronomical Union drew it in 2006 by creating a new category, dwarf planets. To be a planet, an object has to meet 3 criteria. It has to orbit the Sun. It has to be massive enough that its own gravity pulls it into a roughly spherical shape. And it has to have cleared its orbit of other debris. That last criterion is the killer. Pluto has not cleared its orbit. It shares the Kuiper Belt with thousands of other objects, some of them in orbits that cross Pluto's path. Eris has not cleared its orbit either. Neither have the other large Kuiper Belt objects like Makemake or Haumea, so they are not planets. They are dwarf planets. The decision was controversial. A lot of people, including some planetary scientists, think it was arbitrary, but it stuck. Pluto is no longer the 9th planet. It is the largest known dwarf planet in the Kuiper Belt, and it is one of the most geologically active objects in the outer solar system. Nobody expected that. Before 2015, Pluto was just a distant frozen ball of ice and rock, too small and too cold to have any interesting geology. Then NASA's New Horizons spacecraft flew past it in July 2015, and everything changed. The images New Horizons sent back showed a world that was anything but dead. Pluto has mountains made of water ice, towering 3.5 kilometers above the surrounding plains. It has a massive heart-shaped plain called Tombaugh Regio, named after Clyde Tombaugh, made of nitrogen ice that appears to be actively convecting, rising and sinking in slow geologic cycles like a lava lamp. It has a thin atmosphere of nitrogen, methane and carbon monoxide that extends hundreds of kilometers above the surface and is slowly escaping into space. It has surface features that look like they were created by flowing liquids, even though the surface temperature is around -223 degrees Celsius, cold enough that nitrogen freezes solid. Pluto's moon Charon is almost as interesting. It is so large relative to Pluto, about half Pluto's diameter, that the two objects orbit a common center of mass located in the space between them. Technically, Pluto and Charon are a binary system. Charon's surface is covered in water ice and shows signs of past tectonic activity. Long fractures stretch across its surface, evidence that the moon's interior once expanded, possibly because a subsurface ocean froze and the ice took up more volume than the liquid water did. There is no indication that Charon is still active today, but the fact that it was active at all is surprising. Objects this small, this far from the Sun, should have frozen solid billions of years ago. Whatever kept Pluto and Charon warm enough to drive geologic activity is not fully understood. Tidal heating from their mutual orbit is one possibility. Radioactive decay in their interiors is another, or maybe the Kuiper Belt is just stranger than we thought. The New Horizons flyby was a one-shot deal. The spacecraft was traveling at about 14 kilometers per second, too fast to stop or orbit. It flew past Pluto, took as many pictures and measurements as it could in a few hours, and kept going. It is still going. After Pluto, the mission team selected a new target deeper in the Kuiper Belt, a small object designated 2014 MU69 and later named Arakoth. New Horizons reached it on January 1st, 2019, flying past at a distance of about 3,500 kilometers. Arakoth is tiny compared to Pluto, only about 36 kilometers long, and it has a bizarre shape. It looks like two lobes stuck together. A contact binary formed when two separate objects collided gently and merged. The surface is smooth, covered in ancient craters, with almost no signs of geologic activity. Arakoth is a fossil, a pristine sample of the material that was floating around the outer solar system 4.5 billion years ago when the planets were forming. Nothing has happened to it since. It has been sitting in the cold, untouched, a time capsule from the birth of the solar system. That is what makes the Kuiper Belt so valuable scientifically. The objects there are leftovers. They are made of the same material that built the planets, but they never got incorporated into anything larger. They are too far from the sun, too spread out, and too slow-moving to collide and merge efficiently. So they just stayed where they were, drifting in the dark, preserving a record of the conditions in the early solar system. Study the composition of a Kuiper Belt object, and you are studying the raw ingredients that went into making Earth, Mars, Jupiter, all of it. The difference is that Earth has been geologically active for 4.5 billion years. Its surface has been melted, recycled, eroded, covered in oceans and continents. The original material is long gone, buried under layers of processed crust. Kuiper Belt objects have not been processed. They are the original recipe. But the Kuiper Belt is not the edge of the solar system. Not even close. Beyond the Kuiper Belt, much farther out, there is something else. Something we have never directly observed, but are almost certain exists. A vast spherical shell of icy debris surrounding the entire solar system, stretching outward to distances of thousands or even tens of thousands of astronomical units. Astronomers call it the Oort cloud, named after Jan Oort, the Dutch astronomer who first proposed its existence in 1950. The Oort cloud is where the long-period comets come from, the ones that take hundreds or thousands or even millions of years to complete a single orbit around the Sun. And if the models are correct, there are billions of objects in the Oort cloud, possibly trillions, most of them no larger than a few kilometers across. The Oort cloud has never been seen. Not a single object in it has been directly detected. That is because the objects are too small and too far away. Even the largest ones, the ones a few hundred kilometers across, would be far too faint to show up in any telescope we have built. The sunlight reaching the Oort cloud is so weak that even a large, icy body would barely reflect enough light to be detectable from Earth. And the objects are spread out over such an enormous volume of space that the chances of one passing in front of a background star, creating a brief occultation that we could measure, are vanishingly small. So we infer the Oort cloud's existence from the comets it sends our way. Long-period comets have orbits that are nearly parabolic, meaning they come from very far away, swing past the sun once, and then head back out into the dark. When you trace those orbits backward, they point to a source region sitting somewhere between a few thousand and 100,000 astronomical units from the Sun. That is the Oort cloud. To put that distance in perspective, Pluto orbits at about 40 astronomical units. The Kuiper Belt extends out to maybe 100. The inner edge of the Oort cloud is thought to begin around 2,000 astronomical units. The outer edge could be as far out as 100,000 astronomical units. That is roughly 1.5 light years from the Sun, almost halfway to the nearest star. The Sun's gravitational influence extends that far, barely. Objects in the outer Oort cloud are so loosely bound to the Sun that a passing star, even one several light years away, can nudge them, change their orbits, send them falling inward toward the Sun. And that, according to the models, is how long-period comets are created. A star passes near the Oort cloud, its gravity tugs on the icy debris, and a few objects get knocked out of their stable orbits. Some of them fall inward. Some of them get ejected from the solar system entirely, flung off into interstellar space. The ones that fall inward become comets. This happens slowly. Stars do not pass close to the Sun very often. The nearest star, Proxima Centauri, is about 4.2 light years away, and it is not moving toward us. It will stay roughly that distance for a very long time. But over millions of years, other stars do pass relatively close, within a light year or two, close enough to perturb the Oort cloud. And when they do, a shower of comets can be sent into the inner solar system over the course of a few 100,000 years. Some researchers have suggested that mass extinction events on Earth caused by asteroid or comet impacts might be linked to these close stellar encounters. The idea is controversial, the evidence is shaky, but it is at least plausible. If a passing star sent a swarm of comets into the inner solar system, some of them would cross Earth's orbit, a few would hit, and a large enough impact, something a few kilometers across, would be catastrophic, enough to cause a global extinction event. The Oort cloud is also affected by the tidal forces of the Milky Way itself. The galaxy is not uniform, matter is distributed in a disk with spiral arms, and the density of stars and gas varies depending on where you are. The Sun orbits the center of the galaxy once every 230 million years, moving through regions of higher and lower density. When the solar system passes through a dense region, the gravitational pull from all that nearby matter can tug on the outer Oort cloud, triggering a comet shower. This process is called galactic tides, and it is thought to contribute to the steady background rate of long-period comets entering the inner solar system. On top of that, there are molecular clouds, giant clumps of gas and dust drifting through the galaxy. If the solar system passes through or near one of those, the gravitational effect is even stronger. The Sun has been orbiting the galaxy for 4.5 billion years, passing through dozens of molecular clouds and spiral arms. Each time, the Oort cloud gets jostled, comets rain inward. Some of them hit planets, some of them evaporate near the Sun and disappear. The Oort cloud is not static, it is constantly being depleted and possibly replenished by material captured from interstellar space. That last part is speculative. We do not know for certain whether the Oort cloud is gaining or losing mass over time. If it is only losing material, then eventually it will run out. Billions of years from now, there will be no more comets. The long-period comet population will go extinct. But if the Oort cloud is being replenished by capturing icy debris from passing molecular clouds or the interstellar medium, then it could last indefinitely. The solar system is moving through space at about 220 kilometers per second relative to the local standard of rest. That is fast enough to sweep up a significant amount of material over millions of years. Whether that material is dense enough and slow enough to be captured into the Oort cloud is an open question. The models go both ways. Some simulations suggest the Oort cloud is stable on billion-year timescales. Others suggest it is slowly evaporating. The structure of the Oort cloud is also uncertain. Most models divide it into two regions, an inner Oort cloud shaped like a thick torus or donut, and an outer Oort cloud shaped like a spherical shell. The inner Oort cloud is thought to contain objects that formed closer to the Sun, in the region where the giant planets are today, and were scattered outward by gravitational interactions with Jupiter, Saturn, Uranus, and Neptune. The outer Oort cloud contains objects that were scattered even farther, into a region where the Sun's gravity is so weak that the objects are no longer confined to the plane of the solar system. They orbit in every possible direction, forming a sphere. The distinction matters because objects in the inner Oort cloud are more likely to be nudged back into the inner solar system by gravitational perturbations. Objects in the outer Oort cloud are more loosely bound and more likely to be lost to passing stars or galactic tides. No spacecraft has ever visited the Oort cloud. New Horizons is heading in that general direction, but it will not get there for thousands of years. Even if it survives that long, which it will not because its nuclear power source will run out in the 2030s, it will pass through the inner edge of the Oort cloud without detecting anything. The objects are too small and too far apart. You could fly through the Oort cloud for centuries and never come within 1,000,000 kilometers of a single object. Space is empty out there. Not empty in the way the inner solar system is empty, where you can still see the sun and the planets and occasional asteroids drifting by. Empty in the way interstellar space is empty. Dark, cold, silent. The sun is just a bright star, no bigger than Venus looks from Earth. The planets are invisible. There is no sense of being in a solar system anymore. You are on your own, and that is the boundary. The place where the sun's influence fades to almost nothing. Objects in the outer Oort cloud are gravitationally bound to the sun, but barely. A nudge from a passing star is enough to change their orbits. The sun's light is so faint that it provides almost no heat. The temperature of an object in the Oort cloud is only a few degrees above the temperature of interstellar space itself, which is about 3 degrees Kelvin, the temperature of the cosmic microwave background. You are sitting at the edge of a solar system, but you might as well be floating in the void between the stars. The difference is academic. This is the frozen frontier, not because it is covered in ice, though it is, but because it is the place where motion stops, where the solar system runs out of momentum, where everything left over from the formation of the planets has been pushed as far as gravity and orbital mechanics will allow. The Kuiper Belt and the Oort cloud are not destinations. They are the boundary between here and nowhere, between the region of space that belongs to the sun and the region that belongs to the galaxy. And crossing that boundary, leaving the sun's gravity well behind and entering interstellar space, is something only 2 spacecraft have ever done. Both of them launched more than 45 years ago. Both of them are still sending back data, and both of them are now farther from Earth than any human-made object has ever been. They are called Voyager 1 and Voyager 2, and they are the subject of the next part of this story. Two spacecraft are falling through the dark right now. They have been falling for more than 47 years, falling away from the sun, away from the planets, away from everything that could reasonably be called home. They are farther from Earth than any object humanity has ever built. Farther than any signal we have sent, farther than any plan we ever had for them. And they are still talking, still sending data back across a gulf so vast that the radio signals, traveling at the speed of light, take more than 22 hours to reach us. By the time we hear from them, they have already moved millions of miles farther into the void. They are called Voyager 1 and Voyager 2, and they are humanity's first and only emissaries to interstellar space. The story starts in 1977. Not with a grand plan to leave the solar system. That came later. The Voyagers were built for something more practical. A rare alignment of the outer planets, a geometric coincidence that happens once every 176 years, was about to occur. Jupiter, Saturn, Uranus, and Neptune were going to line up in such a way that a spacecraft could visit all 4 of them using gravity assists, slingshotting from one planet to the next without needing enormous amounts of fuel. The window opened in the late 1970s and closed by the early 1980s. Miss it, and you would have to wait until the 22nd century for another chance. NASA called it the Grand Tour, and the Voyagers were designed to take it. Voyager 2 launched first, on August 20th, 1977, from Cape Canaveral. Voyager 1 launched 16 days later, on September 5th. The naming is backwards because Voyager 1 was on a faster trajectory. It would reach Jupiter and Saturn before its twin, even though it launched second. Both spacecraft were identical. Each one weighed about 825 kilograms, roughly the size of a small car. They carried cameras, spectrometers, magnetometers, plasma detectors, and a dish antenna pointed back toward Earth. Power came from 3 radioisotope thermoelectric generators, RTGs, essentially nuclear batteries that convert the heat from decaying plutonium into electricity. No solar panels. The outer planets are too far from the Sun for solar power to be practical. The RTGs were built to last, and they have. The Grand Tour worked. Voyager 1 flew past Jupiter in March 1979, capturing the first detailed images of the planet's swirling cloud bands and discovering active volcanoes on its moon Io, something no one had predicted. Then it flew past Saturn in November 1980, photographing the planet's rings in unprecedented detail and revealing the strange hexagonal storm at Saturn's North Pole. After Saturn, Voyager 1's trajectory sent it upward, out of the plane of the solar system, aimed toward the stars. Its planetary tour was over. Voyager 2 took a different path. It flew past Jupiter in July 1979, then Saturn in August 1981. But its trajectory kept it in the plane of the solar system, allowing it to continue to Uranus, which it reached in January 1986, and Neptune, which it reached in August 1989. Voyager 2 is still the only spacecraft to have visited Uranus and Neptune. The images it sent back are the only close-up views we have of those worlds, Neptune's great dark spot. Uranus tipped on its side, rolling through its orbit like a barrel, the geysers on Neptune's moon Triton, spouting nitrogen gas into space. None of this had been seen before. Voyager 2 was the scout, the first, and so far the only visitor to the farthest reaches of the planetary solar system. After Neptune, both spacecraft had completed their primary missions. The cameras were still working, the instruments were still collecting data, but there were no more planets to visit. The spacecraft were heading outward, away from the Sun, into a region of space where nothing had ever been. NASA could have shut them down, declared victory, moved on. Instead, the mission was extended. The new objective was simple: keep going. See what is out there. Find the edge of the Sun's influence and cross it. Become the first human-made objects to enter interstellar space. That edge is called the heliopause. To understand what it is, you need to understand the heliosphere. The Sun is not a quiet ball of gas sitting in space. It is actively spewing material outward in every direction. A stream of charged particles, mostly electrons and protons, blasts away from the Sun's surface at speeds of about 400 kilometers per second. This is the solar wind. It is not wind in the way we think of wind on Earth, moving air from one place to another. It is a plasma, a superheated gas where the electrons have been stripped away from the atoms, creating a flow of electrically charged particles. The solar wind carries the Sun's magnetic field with it, stretching the field lines outward like the spokes of an umbrella being blown inside out by a storm. The solar wind does not stop at any particular distance. It just keeps going, expanding outward, getting thinner and weaker as it spreads across a larger and larger volume of space. But eventually, it runs into something: the interstellar medium, the thin gas that fills the space between the stars. That gas is mostly hydrogen, with traces of helium and heavier elements. It is incredibly thin, only a few atoms per cubic centimeter, but it is there, and it pushes back. The solar wind slams into the interstellar medium, and the two plasmas collide. The result is a boundary. A place where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. That boundary is the heliopause, and it defines the edge of the heliosphere, the bubble of space dominated by the Sun's influence. The heliosphere is not spherical, it is more like a comet. The Sun is moving through the galaxy at about 220 kilometers per second relative to the local interstellar medium. That motion creates a bow shock, a compressed region of space ahead of the Sun where the interstellar medium is piling up. Behind the Sun, the heliosphere stretches out into a long tail, blown backward by the relative motion. The entire structure is enormous. The distance from the Sun to the heliopause is about 120 astronomical units in the direction the Sun is moving. That is roughly 11 billion miles. In the opposite direction, the tail of the heliosphere stretches much farther, possibly hundreds of astronomical units. For decades, scientists could only model the heliosphere. They knew it had to exist. The physics demanded it. But no spacecraft had ever reached it. No instrument had ever measured it directly. The Voyagers were going to change that. As the spacecraft moved outward through the 1990s and 2000s, they were traveling through a region called the heliosheath. This is the outer layer of the heliosphere, the place where the solar wind has slowed down and is being deflected around the heliopause, like water flowing around a rock in a stream. The solar wind in the heliosheath is turbulent, chaotic. The magnetic field lines twist and tangle. The plasma density fluctuates. The Voyagers could measure all of this, and the data they sent back showed that the heliosheath was more complex than the models predicted. Then, in August 2012, Voyager 1's instruments detected a sudden change. The number of high-energy particles, cosmic rays from outside the solar system, jumped sharply. At the same time, the number of low-energy particles from the Sun dropped to nearly zero. The magnetic field strength increased. The plasma environment changed completely. Voyager 1 had crossed the heliopause. It had left the heliosphere and entered interstellar space. The announcement was made in September 2013 after months of analysis to confirm the measurements. Voyager 1 was the first human-made object to leave the Sun's protective bubble. It was now traveling through the space between the stars. Voyager 2 followed 6 years later. In November 2018, it crossed the heliopause at a different location, about 119 astronomical units from the Sun. The crossing was similar to Voyager 1's, but not identical. The magnetic field orientation was slightly different. The plasma density was higher. The transition was sharper. These differences are important because they tell scientists that the heliopause is not uniform. It varies depending on where you cross it and when. The Sun's activity changes on an 11-year cycle, and that affects the solar wind's strength. The interstellar medium is not uniform either. It has its own structure, its own density variations. The heliopause shifts and ripples in response to all of this. Voyager 1 and 2 crossed at different times and different places, and their measurements show that the boundary is dynamic, constantly changing. The fact that both spacecraft are still sending data is remarkable. They were not built to last this long. The RTGs lose power every year as the plutonium decays. When the mission started, each RTG produced about 470 watts. Today, they produce less than 250. That is not enough to run all the instruments. NASA has been shutting systems down one by one to conserve power. Heaters were turned off first, then some of the instruments. The cameras were shut down in 1990 after Voyager 2's Neptune flyby because there was nothing left to photograph and the data storage was needed for other instruments. The ultraviolet spectrometer was turned off. The planetary radio astronomy instrument was turned off. What remains are the instruments that can measure the interstellar environment: the magnetometer, the plasma wave instrument, the cosmic ray detector, the low-energy charged particle detector. These are still running, and they will keep running until the RTGs no longer produce enough power to operate the spacecraft's transmitter. That will happen sometime in the 2030s, maybe 2036, maybe a little earlier. When the power finally drops below a critical threshold, the spacecraft will stop sending signals. They will keep moving. Nothing can stop them. But we will lose contact. The Voyagers will become silent, drifting through the galaxy, carrying their data with them into the dark. But before that happens, they are giving us the first direct measurements of the space between the stars, and what they are finding is both familiar and strange. Interstellar space is not empty. It is filled with a thin plasma, the interstellar medium, and it is threaded with magnetic fields. The density is only about 0.1 particles per cubic centimeter. That is 1,000,000 times thinner than the best vacuum we can create on Earth, but it is not zero. The magnetic field strength is about 0.4 nanotesla. That is incredibly weak, about 100,000 times weaker than Earth's magnetic field. But it is there, and it has structure. The field lines are aligned in a particular direction, running roughly parallel to the plane of the galaxy. The Voyagers are measuring the orientation of those field lines, and the data is surprising. The magnetic field in the interstellar medium is aligned more closely with the Sun's magnetic field than the models predicted. That suggests the heliopause is not a sharp boundary where everything changes abruptly. It is a transition region where the solar magnetic field and the interstellar magnetic field interact and partially merge. The cosmic ray flux is also interesting. Cosmic rays are high-energy particles, mostly protons, that zip through the galaxy at nearly the speed of light. They are produced by supernova explosions, by the acceleration of particles in the magnetic fields around neutron stars and black holes, by processes we do not fully understand. The heliosphere shields the inner solar system from most cosmic rays. The solar wind and the Sun's magnetic field deflect them, keeping the radiation dose at Earth relatively low. But outside the heliosphere, there is no shield. The cosmic ray flux jumps by a factor of about 3. That is a problem for any future mission that tries to send humans beyond the heliopause. The radiation dose would be high, very high. Without heavy shielding, a crew would be exposed to radiation levels that could cause cancer, damage the central nervous system, and degrade electronic equipment. The Voyagers are robots. They do not care about radiation, but humans would. The plasma wave instrument has also picked up something unexpected: faint oscillations in the plasma density caused by shock waves from distant supernova or the turbulence of the interstellar medium itself. These waves are incredibly faint. The amplitude is measured in fractions of a particle per cubic centimeter, but the instrument is sensitive enough to detect them. And by measuring the frequency and speed of these waves, scientists can calculate the density of the plasma around the spacecraft. That density has been slowly increasing as the Voyagers move farther from the heliopause. The interstellar medium is not uniform. It has regions that are denser and regions that are thinner. The Voyagers are entering a denser region. Eventually they will pass through it and enter a thinner one. The journey will continue. The data will keep coming until it does not. But the Voyagers are more than just scientific instruments. They are also messages. Both spacecraft carry a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. The record was curated by a committee chaired by Carl Sagan, the astronomer and science communicator who spent much of his career thinking about the possibility of life elsewhere in the universe and how we might communicate with it. The golden record was not meant to be found. The chances of either Voyager encountering another civilization are vanishingly small. Space is vast. The spacecraft are moving at about 17 kilometers per second relative to the Sun, which sounds fast but is a crawl on galactic scales. It will take about 40,000 years for Voyager 1 to pass within about 1.5 light-years of a star called Gliese 445. By that time, the spacecraft will be long dead. Its transmitter will have stopped working. Its instruments will be frozen. It will just be a piece of metal and plastic and wiring tumbling silently through the dark. But if someone does find it, if some future civilization intercepts one of the Voyagers 1,000,000 years from now, or 1,000,000,000, the golden record will still be there. The record contains 116 images, encoded as analog signals, pictures of Earth, oceans, forests, mountains, cities, pictures of people, a man and a woman, a baby, a family, pictures of animals, a snake, an eagle, a dolphin, pictures of human achievements, the Great Wall of China, the Golden Gate Bridge, a rocket launch. The images are not meant to be comprehensive. They are meant to be representative. A snapshot of what Earth and humanity looked like in 1977. The record also contains sounds, greetings in 55 languages, a message from then United Nations Secretary-General Kurt Waldheim, a message from then United States President Jimmy Carter, natural sounds, wind, rain, thunder, surf, birdsong, whale song, human sounds, footsteps, laughter, a kiss, a heartbeat, music, 90 minutes of music from cultures around the world, Bach, Beethoven, Mozart, Chuck Berry, a Navajo chant, a Japanese shakuhachi, a Peruvian panpipe. The music was chosen to represent the diversity of human culture. The idea was that if anyone ever finds the record and figures out how to play it, they will hear something of what it means to be human, or at least what it meant in 1977. The golden record is a time capsule, but it is also a message of hope. Carl Sagan wrote in the liner notes that the record was intended to communicate one thing above all: that humanity existed, that we were here, that we looked out at the stars and wondered if anyone else was out there, and that we tried to say hello, even if no one ever hears it. Even if the Voyagers drift for billions of years through the galaxy without ever coming close to another world, the record is proof that we tried, that we thought it was worth doing. The cover of the golden record contains instructions for how to play it, etched into the gold-plated surface. A diagram of a record player, a stylus, the speed at which the record should be played, a map showing the location of the Sun relative to 14 pulsars, neutron stars that emit regular pulses of radio waves. The pulsar map is a kind of cosmic address. If anyone finds the record and recognizes the pulsars, they can use the map to figure out where the Sun is. The pulsar periods are given in binary, and the map includes a reference to the hydrogen spin-flip transition, a universal constant that any technologically advanced civilization should recognize. It is a message designed to be understood by someone who does not speak any human language. Whether it will ever be found is another question. The odds are not good. The galaxy contains hundreds of billions of stars. The Voyagers are two tiny objects moving through a volume of space so vast that even if every star had a dozen planets, the chances of the spacecraft passing close to any of them are almost zero. And that assumes other civilizations exist, that they are out there, that they are looking, that they care. All of those assumptions are uncertain. We have no evidence that life exists anywhere else in the universe. We have no evidence that intelligence arises anywhere but here. The Voyagers could drift for trillions of years without ever encountering anything but dust and gas and empty space. The golden record could remain unplayed forever, but the message was not really for aliens, it was for us. The golden record is a statement about who we are, about what we value, about the idea that we are part of something larger than ourselves. Carl Sagan said it best: the spacecraft will be encountered, and the record will be played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. That bottle is still traveling. Right now, as you are reading this, Voyager 1 is about 24 billion kilometers from Earth. Voyager 2 is about 20 billion kilometers away. Both are moving outward at more than 3 astronomical units per year. They will never stop. They will never turn around. They have escaped the sun's gravity well completely. They are on trajectories that will carry them out of the solar system and into the galaxy. In 40,000 years, Voyager 1 will pass near Gliese 445. In 300,000 years, it will reach the distance of the nearest stars in our current neighborhood. In a few million years, both spacecraft will have traveled far enough that the sun will just be another star in the sky. Faint, unremarkable, indistinguishable from the hundreds of billions of other stars scattered across the Milky Way. And the galaxy itself is just one of hundreds of billions of galaxies in the observable universe. A tiny island of stars and gas floating in a void so vast that light takes billions of years to cross it. The Voyagers have left the solar system, but the solar system is a speck. The sun is one star among hundreds of billions in a galaxy that is itself one of hundreds of billions. The journey the Voyagers have taken from Earth to interstellar space is a monumental achievement by human standards. By cosmic standards, they have barely moved. They are still inside the Milky Way, still inside the local group of galaxies, still inside the Virgo supercluster, still inside a universe that extends outward for 46 billion light-years in every direction. The edge the Voyagers crossed, the heliopause, is not the edge of everything. It is just the edge of the sun's influence, the edge of the region where the solar wind dominates. Beyond that, there is the interstellar medium. Beyond that, the space between galaxies. Beyond that, the space between galaxy clusters. And beyond that, the edge of the observable universe itself, a boundary defined not by any physical barrier, but by time. The limit beyond which light has not had time to reach us, the cosmic horizon. The Voyagers have crossed one boundary. Humanity has sent 2 messengers into the space between the stars, but there are other boundaries, larger ones, stranger ones, boundaries that are not just physical but conceptual. The edge of what we can see, the edge of what we can know, the edge of what the universe allows us to observe. And beyond that edge, there is more, much more, possibly an infinite amount more. A cosmos so vast that everything we have ever seen, every galaxy in every deep field image, every star in the night sky, every planet, every speck of dust, is just a tiny fraction of what exists. The observable universe is not the universe, it is just the part we can see, the part where light has had time to reach us. Beyond the observable universe, the cosmos continues. How far, we do not know. What it contains, we do not know. Whether it is finite or infinite, we do not know. But it is out there. And the next part of this story is about what might lie beyond the edge of everything we can observe, beyond the cosmic horizon, in the infinite darkness that stretches past the limits of light itself. The Voyagers crossed a line in space. They left the bubble of the sun's influence and entered the thin plasma that fills the space between stars. That boundary, the heliopause, is real. It is measurable. You can point to it on a chart and say, here, this is where the solar wind stops and interstellar space begins. It is the edge of something, but it is not the edge of everything, not even close. There is another edge, a much larger one. A boundary that sits not between the sun and the galaxy, but between everything we can possibly observe and everything we cannot. Between the part of the universe where light has had time to reach us and the part where it has not. Between the knowable and the unknowable. This edge is called the cosmic horizon, and it sits roughly 46.5 billion light-years away in every direction. Past that line, the universe continues. We just cannot see it. We cannot measure it. We cannot interact with it in any way. It is beyond the reach of light itself, and light is the fastest thing there is. If you cannot send or receive light from a place, that place might as well not exist, except it does. This is where cosmology stops being about what we can observe and starts being about what we can infer, what we can deduce from the rules of physics and the behavior of the universe we do see. And the conclusions are strange, unsettling in ways that distant galaxies and black holes and interstellar voids are not, because those things are at least visible. They are out there in the data. You can point a telescope at them and measure their properties. What lies beyond the cosmic horizon is not out there in the data. It is out there in the math. And the math says the universe is almost certainly bigger than the part we can see, possibly much bigger, possibly infinitely bigger. Start with the simplest question. If the universe is 13.8 billion years old, why is the farthest thing we can see not 13.8 billion light-years away? Light travels at a fixed speed, 300,000 kilometers per second. Nothing moves faster. If the universe has been around for 13.8 billion years, then the farthest light could have traveled is 13.8 billion light-years. That should be the edge. The cosmic horizon should sit 13.8 billion light-years from Earth in every direction. The observable universe should be a sphere about 27.5 billion light-years across. Simple, clean, wrong. The actual number is 93 billion light-years across. The cosmic horizon sits at about 46.5 billion light-years, not 13.8. That is more than 3 times farther than the age of the universe multiplied by the speed of light would predict. The gap is not a rounding error. It is not a measurement mistake. It is real, and it exists because space itself has been expanding the entire time that light has been traveling toward us. The light from a distant galaxy that has been traveling for 13.8 billion years has been traveling through space that was stretching the whole time. By the time the light reaches Earth, the galaxy that emitted it is no longer where it was when the light left. It has been carried away by the expansion of space to a distance of more than 46 billion light-years. This is not intuitive. Distance, in our everyday experience, is fixed. If something is a mile away and you walk toward it, the distance shrinks. If you walk away, the distance grows, but the object itself does not move. Space stays still. In cosmology, space does not stay still. It expands, and it has been expanding since the moment the universe began. The expansion is not objects moving through space. It is space itself growing, stretching, creating more distance between objects that are not moving at all relative to their local surroundings. A galaxy sitting 46 billion light-years away is not traveling through space at faster than light speed. It is sitting still or close to it. But the space between us and that galaxy has been expanding for 13.8 billion years, and the accumulated stretching has carried the galaxy to its current distance. The result is a universe where the observable region is far larger than you would naively expect. And here is the uncomfortable part. That observable region, the 93 billion light-year wide sphere centered on Earth, is almost certainly not the whole thing. It is just the part we can see, the part where light has had time to reach us. The universe beyond that boundary, the part past the cosmic horizon, is still there. It is still expanding. It still contains galaxies, stars, planets, all the same structures we see inside the observable universe. We just cannot see it because the light has not arrived yet. And depending on how fast the expansion is accelerating, some of that light may never arrive. So how big is the actual universe? The entire thing, not just the part we can observe. Nobody knows. The observable universe is the only part we have direct access to. Everything beyond the horizon is inference. The simplest possibility is that the universe is infinite, that it goes on forever in every direction, filled with galaxies and stars and voids, stretching endlessly with no boundary and no edge. That would make the observable universe a tiny finite bubble sitting inside an infinite expanse, like a sphere of light in an infinite dark room. You can see everything inside the sphere, but the room goes on forever beyond it. Is that true? Is the universe actually infinite? The data does not give a clear answer. Measurements of the cosmic microwave background, the faint afterglow of the Big Bang, show that the universe is flat, or very close to it. Flat, in cosmological terms, does not mean two-dimensional. It means the geometry of space follows the rules of ordinary Euclidean geometry. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. A flat universe can be infinite. It does not have to curve back on itself the way a sphere does. If the universe is perfectly flat, and the measurements suggest it is within a tiny margin of error, then it could extend forever. Infinite space, infinite galaxies, infinite stars, infinite copies of every structure, including, eventually, infinite copies of you. That last part is not a poetic flourish, it is a consequence of the math. In an infinite universe with a finite number of possible arrangements of matter, every possible arrangement must eventually repeat. There are only so many ways to arrange atoms in a given volume of space. The number is enormous, but it is finite. If space goes on forever, then every arrangement, no matter how unlikely, will occur not just once, but infinitely many times. That includes the exact arrangement of atoms that make up you, sitting in the exact arrangement that makes up your room, on the exact arrangement that makes up Earth. Somewhere out there, in an infinite universe, there is another version of you, identical down to the atomic level, reading this exact sentence at this exact moment, and another, infinitely many copies, scattered across infinite space. This is not science fiction. This is what the math predicts, if the universe is truly infinite and truly uniform. Most cosmologists find the idea uncomfortable, not because it is wrong, but because it is untestable. You can never observe those copies. They are beyond the cosmic horizon, separated from you by distances so vast that no signal will ever pass between you. They exist, if they exist, in a region of space that is permanently disconnected from ours. You will never meet them. You will never communicate with them. They will never know you exist, and you will never know they exist. The prediction is unfalsifiable, which makes it scientifically frustrating, but the math says it should be true. The alternative is that the universe is finite, not infinite, but still without an edge. This sounds contradictory, but it is not. Think of the surface of a sphere. If you walk in any direction on the surface of Earth, you will never hit a wall. You will never fall off an edge. You can walk forever and never reach a boundary. But the surface of Earth is finite. It has a total area. It is finite but unbounded. A finite universe could work the same way in 3 dimensions. You could travel in any direction forever and never hit a wall, but the total volume of space would still be finite. The geometry would be curved in a way that wraps space back on itself, like the surface of a sphere, but extended into an extra dimension we cannot visualize. The measurements of the cosmic microwave background rule out strong curvature. If the universe is finite, it is very large enough that the curvature is almost undetectable. The observable universe would sit inside it like a tiny flat patch on the surface of an enormous sphere. Zoom in close enough and the sphere looks flat. Zoom out far enough and you would see the curvature. But we cannot zoom out. We are stuck inside the observable region, looking at a patch too small to reveal the overall shape. The data is consistent with a flat, infinite universe. It is also consistent with a very large, finite universe with very gentle curvature. We cannot tell the difference. Then there is inflation, the theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation is not just a guess. It is the leading explanation for several features of the universe that would otherwise be coincidences. The cosmic microwave background is almost perfectly uniform. The temperature varies by only a few parts per 100,000 from one side of the sky to the other. That uniformity is strange because the regions on opposite sides of the sky are so far apart that light has never had time to travel between them. They have never been in contact. So how did they end up at the same temperature? The only way to get that level of uniformity is if those regions were once much closer together, close enough to exchange energy and reach thermal equilibrium, and then were suddenly blown apart faster than light could keep them in contact. Inflation does exactly that. It takes a tiny patch of space, smaller than an atom, and stretches it to a size larger than the observable universe in a fraction of a second. The expansion is so fast that regions once in contact get pulled apart to distances where they can no longer communicate. Inflation explains the uniformity. It also explains why the universe is so flat. A curved space, if you stretch it enough, looks flat. Blow up a balloon and the surface is obviously curved. Blow it up to the size of a planet and the surface looks flat to anyone standing on it. Inflate space by a factor of 10 to the 26 or more, which is what inflationary models predict, and even a strongly curved universe would look flat within the observable region. The curvature would still be there, but it would be stretched out over scales far larger than we can see. Inflation makes flatness almost inevitable, and flatness is what we observe. But inflation has a consequence. If the universe inflated by a factor of 10 to the 26 or more, then the part we can see, the observable universe, is just a tiny speck inside a much larger inflated region. The region that inflated is at least 10 to the 26 times bigger than the observable universe. That is a 1 followed by 26 zeros, a number so large it is almost meaningless. The entire observable universe, every galaxy we have ever seen or ever will see, sits inside a volume of space that is itself a tiny fraction of the region that underwent inflation. And that region, according to some versions of inflation, is itself a tiny fraction of a larger space where inflation is still happening in some places but not others. This is where the idea of a multiverse comes in. Not multiple universes in the science fiction sense of parallel dimensions or alternate timelines. A multiverse in the sense that inflation, once it starts, may never fully stop everywhere. It stops in some regions like ours, creating pockets of space where the rapid expansion ends and matter and energy settle into a more familiar form. Stars, galaxies, planets. But in other regions, inflation keeps going. And those inflating regions can spawn new pockets where inflation stops, creating more bubble universes. Each bubble is its own observable universe, with its own galaxies, its own stars, its own version of physics potentially, depending on how the details shake out. The bubbles are separated by regions of space that are still inflating, expanding so fast that no signal from one bubble can ever reach another. Each bubble is a universe unto itself, causally disconnected from the others. This is not established science. This is speculative cosmology, sitting at the edge of what theory allows and what observation can test. The multiverse idea comes out of certain models of inflation, but not all models predict it, and even in the models that do, there is no way to test it directly. By definition, the other bubbles are beyond our cosmic horizon. We cannot see them, we cannot interact with them, we cannot measure their properties. The only evidence for a multiverse would be indirect, something like a faint pattern in the cosmic microwave background that could be interpreted as the imprint of a collision with another bubble early in our universe's history. Astronomers have looked for those patterns. They have not found anything convincing. The multiverse remains a hypothesis, not a confirmed fact, but the possibility is there. And if it is true, it changes the scale of existence in a way that makes the observable universe look almost trivially small. Imagine a volume of space containing not one observable universe, but an infinite number of them, each one a bubble 93 billion light-years across, filled with hundreds of billions of galaxies, each galaxy containing hundreds of billions of stars. Each bubble separated from the others by inflating space, forever out of reach. Some of those bubbles might have different physical constants, different strengths of gravity, different masses for fundamental particles, different rules for how forces interact. Most of those bubbles would be sterile, unable to form stars or galaxies or anything interesting. A universe where gravity is too strong collapses back on itself before stars can form. A universe where the electromagnetic force is too weak cannot hold atoms together. The bubbles that do support complexity, that allow stars and chemistry and possibly life, would be rare. But in an infinite multiverse, rare is not the same as unique. There could be countless bubbles like ours, scattered across an eternally inflating expanse, each one a universe in its own right. This is the logical endpoint of pushing cosmology to its limits. You start with the observable universe. You realize it is just the part where light has had time to reach us. You infer that space extends beyond the cosmic horizon, possibly forever. You add inflation and end up with a vast inflated region far larger than the observable universe. You take inflation seriously and end up with eternal inflation, a process that never fully stops, spawning bubble after bubble in an endless cascade. The scale explodes at every step. The universe is not just bigger than it looks. It might be unimaginably, incomprehensibly bigger. And the part we can see, the 93 billion light-year wide sphere we call the observable universe, might be an infinitesimal speck in a structure so vast that no analogy does it justice. The human mind is not built for this. We evolved to navigate a world measured in meters and kilometers, a world where distances are fixed, where the horizon is the limit of vision, where the sky above is a dome we will never reach. The scale of the universe, even the observable part, strains comprehension. Add the possibility of infinite space beyond the horizon, or a multiverse of bubble universes beyond that, and the whole thing becomes abstract. Numbers on a page, mathematical predictions disconnected from anything we can touch or see or experience. And yet the math is there, the logic is there. The observations, limited as they are, point in that direction. There is no edge to the universe in the way most people think of an edge. No wall, no barrier, no place where space stops. The cosmic horizon is not a physical boundary. It is a limit imposed by the speed of light and the age of the universe. An informational edge, not a structural one. Cross the horizon and space continues, galaxies continue, stars continue. The universe does not stop, it just stops being observable. And that distinction between what exists and what we can see is the core tension of modern cosmology. The universe is bigger than the part we can access, possibly far bigger, and the part we cannot access is not some exotic other realm. It is just more of the same. More galaxies, more stars, more voids, more structure, extending outward in every direction to distances we will never measure. Does this matter? In a practical sense, no. The galaxies beyond the cosmic horizon will never affect us. We will never visit them. We will never communicate with civilizations there, if any exist. They are as inaccessible as the past. In a philosophical sense, yes. The realization that the universe is larger than the observable universe, that there is more out there than we can ever see, shifts the frame. It makes the observable universe finite, not in the sense of being bounded, but in the sense of being incomplete. A sample, not the whole. A window, not the room. And it raises the uncomfortable question of what else might be true that we cannot observe. What other structures, what other scales, what other layers of reality might exist beyond the reach of telescopes and light? The limits of observation are not the limits of existence. That is the core insight here. We can only see so far. Light has only had so much time to travel. The expansion of space has only stretched the observable region to a certain size, but the universe itself, the actual physical cosmos, is not constrained by what we can see. It keeps going. And the rules we infer from the part we can see, the laws of physics, the behavior of matter and energy, almost certainly apply to the part we cannot. There is no reason to think the universe beyond the horizon is fundamentally different from the universe within it. It is just farther away. Too far for light to have reached us yet. And because of the accelerating expansion of space, some of it will remain forever beyond reach. The cosmic horizon is not moving outward fast enough to catch up to the galaxies that are being carried away by expansion. They are slipping past the point of no return, crossing into a region of space where their light will never reach us, no matter how long we wait. That process is happening right now. Galaxies at the edge of the observable universe are receding faster than the speed of light, carried by the expansion of space itself. In a few billion years, they will have crossed the horizon permanently. Their light will still be arriving for a while, stretched and red-shifted and fading, but eventually even that will stop. The observable universe will shrink, not because space is contracting, but because the objects we can see are being carried beyond the range where their light can reach us. Future civilizations, if any exist trillions of years from now, will look up and see almost nothing. The Milky Way and a few dozen nearby galaxies, gravitationally bound into a small cluster, will be all that remains visible. The rest of the universe will have vanished beyond the horizon, carried away by the relentless expansion of space. Those future astronomers will have no way of knowing that billions of galaxies once filled the sky. The evidence will be gone. The universe will have hidden its own history. We live in a lucky era. The universe is old enough that galaxies have formed, and light from the most distant ones has had time to reach us. But it is young enough that the acceleration has not yet carried everything beyond the horizon. We can still see the edge. We can still map the observable universe, trace its structure, study its history. In a sense, we are living at the peak of cosmic visibility. The window is open, but it is closing, slowly, over billions of years, but closing nonetheless. The universe is not static. It is changing, expanding, accelerating, and the part we can observe is shrinking, not in physical size, but in the number of galaxies it contains. The cosmic horizon is a one-way door. Once an object crosses it, it is gone. We will never see it again. That makes the question of what lies beyond all the more urgent. Not because we can ever visit it, not because it will ever affect us directly, but because the answer shapes our understanding of what kind of universe we live in. Is the cosmos a finite sphere, bounded by the reach of light, or is it an infinite expanse, stretching forever in all directions? Is the observable universe a representative sample of the whole, or is it a tiny atypical pocket in a larger structure? Are we living in one bubble among many, or is our universe the only one? These questions do not have observational answers, not yet, maybe not ever, but they are not idle speculation. They are the logical extension of taking cosmology seriously, of following the evidence and the math wherever they lead, and where they lead is unsettling. The universe is bigger than we thought, possibly much bigger, possibly infinitely bigger. The part we can see is a speck. The part we cannot see dwarfs it. And the boundary between the two, the cosmic horizon, is not a wall or a limit or a place where things end. It is just the point where light runs out of time, where the expansion of space outraces the speed of information, where the knowable gives way to the unknowable, not because the universe stops, but because our ability to observe it does. The cosmic horizon is a horizon of knowledge, not of existence, and beyond it, the universe goes on. How far, we do not know. What it contains, we cannot measure, but it is there, vast, dark, unreachable, and real. This is where the discussion shifts. We have talked about what we can see and what we cannot. We have talked about the scale of space, the expansion of the universe, the limits of light. But there is another kind of unknown. Not the unknown of distance, but the unknown of substance. Most of the universe, even the part we can observe, is made of things we do not understand. Things we cannot see directly, things we only know about because of the way they affect the matter and light we can see. Dark matter, dark energy, the invisible majority. The next chapter is about them. The universe goes on forever beyond the horizon. Possibly. The math allows it. The observations do not rule it out. And if it is true, then the part we can see is an infinitesimal speck in an infinite expanse. But here is the uncomfortable part. Even within that speck, even within the 93 billion light-year wide sphere we call the observable universe, we do not actually know what most of it is made of. Not in the sense that we are still cataloging all the galaxies. We have done that. Not in the sense that we need better telescopes to see the faint stuff. We have those. In the sense that most of the universe is made of something we cannot see, cannot touch, cannot detect directly with any instrument we have ever built. Something invisible. Something that does not emit light, does not absorb light, does not interact with ordinary matter in any way except through gravity. And it is not a small fraction. It is not a trace contaminant that cosmologists are politely ignoring until they have time to deal with it. It is the majority. Roughly 85% of all the matter in the universe is this invisible stuff. Astronomers call it dark matter, and after nearly a century of searching, no one has any idea what it actually is. The evidence for dark matter is overwhelming. It is not a fringe theory. It is not contested. Every observation astronomers make of the large-scale structure of the universe points to the existence of something massive, something gravitationally influential, that is not showing up in any of the wavelengths of light we can detect. The first hint came in the 1930s from a Swiss astronomer named Fritz Zwicky. Zwicky was studying the Coma cluster, a large collection of galaxies about 300 million light-years from Earth. He measured how fast the individual galaxies in the cluster were moving relative to each other. Galaxies in a cluster are gravitationally bound. They orbit around the cluster's center of mass the way planets orbit the Sun. The speed of those orbits depends on the total mass of the cluster. More mass means stronger gravity, which means the galaxies have to move faster to avoid falling inward. Zwicky measured the speeds and used them to calculate the total mass of the cluster. Then he added up all the visible mass, all the stars in all the galaxies he could see. The numbers did not match. The galaxies were moving far too fast. The visible mass was not nearly enough to hold the cluster together. By Zwicky's calculations, the cluster should have flown apart billions of years ago, but it was still there, stable, intact. Something was holding it together. Something with a lot of mass, something he could not see. Zwicky proposed that the cluster contained a large amount of unsichtbare materia, invisible matter, providing the extra gravity needed to keep the galaxies bound. He estimated that the invisible matter outweighed the visible matter by at least 10 to 1. Nobody believed him. Zwicky had a reputation for being difficult, abrasive, and prone to making bold claims that other astronomers could not verify. His dark matter idea was dismissed as speculative. Maybe he had made a mistake in his measurements. Maybe the galaxies were not actually moving that fast. Maybe there was ordinary matter mixed in with the galaxies, gas and dust too faint to detect, that accounted for the missing mass. The idea sat on a shelf for decades. Then, in the 1970s, an astronomer named Vera Rubin at the Carnegie Institution started measuring the rotation curves of spiral galaxies. A rotation curve is just a graph showing how fast different parts of a galaxy are spinning. In a typical spiral galaxy like the Milky Way, most of the visible mass is concentrated near the center. Stars, gas, dust, all clumped together in the bright bulge at the core. The outer regions, the spiral arms, are much less dense, far fewer stars, far less mass. Newton's laws predict that objects farther from the center of mass should orbit more slowly, just like the planets in the solar system. Mercury orbits fast because it is close to the Sun's gravitational pull. Neptune orbits slowly because it is far away. The same logic should apply to stars in a galaxy. Stars near the center should orbit quickly. Stars in the outer regions should orbit slowly. The rotation curve should drop off as you move outward from the core. Rubin measured the rotation curves of dozens of spiral galaxies using spectroscopy, analyzing the Doppler shifts of light from stars and gas clouds at different distances from the galactic center. The results were consistent across every galaxy she looked at. The rotation curves did not drop off. They stayed flat. Stars in the outer regions of galaxies were orbiting just as fast as stars near the center. Some were even orbiting faster. That should not be possible unless there is a lot more mass out there than the visible stars and gas can account for. A lot more. Rubin's measurements implied that spiral galaxies are embedded in enormous halos of invisible matter, extending far beyond the visible disk. The halos contain several times more mass than all the stars and gas combined, and whatever that mass is made of, it is not emitting light. It is not absorbing light. It is not showing up in any wavelength astronomers can detect. The same pattern shows up everywhere. Galaxy clusters like the ones Zwicky studied, individual galaxies like the ones Rubin measured, even the large-scale structure of the universe, the cosmic web of filaments and voids that spans billions of light-years, simulations of how that structure formed, starting from the tiny density fluctuations in the cosmic microwave background and running forward through billions of years of gravitational collapse, do not work without dark matter. If you try to run the simulation with only ordinary matter, only the stuff we can see, the universe does not clump together fast enough. Galaxies take too long to form. The structure is too smooth, too uniform. It does not match what we observe. Add dark matter, and the simulation works. The invisible halos of dark matter collapse first, pulling ordinary matter into them. The ordinary matter falls into the dark matter's gravitational wells, heats up, forms stars, and lights up as galaxies. The dark matter itself stays dark. It does not interact with light. It just sits there, providing the scaffolding on which the visible universe is built. The evidence is not just gravitational. There is also gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of the cluster bends the light, acting like a lens. The effect was predicted by Einstein's general relativity and confirmed in the early 20th century. Astronomers use gravitational lensing to map the mass distribution in galaxy clusters. They look at how the background galaxies are distorted, stretched into arcs, or smeared into rings, and work backward to figure out where the mass is. What they find is that the mass does not line up with the light. The strongest lensing, The places where gravity is bending light the most are not where the galaxies are. They are in the spaces between the galaxies, in regions where there is almost no visible matter at all. The only explanation is that most of the mass is invisible. Dark matter, distributed in clumps and filaments throughout the cluster, is doing most of the lensing. The bullet cluster is the most dramatic example. It is actually two galaxy clusters that collided with each other a few 100 million years ago. When the clusters smashed together, the galaxies passed through each other mostly unscathed because the distances between stars are so vast that direct collisions are rare. But the hot gas filling the space between the galaxies, gas that is dense enough to glow in X-rays, slammed into itself and piled up in the middle, heated by the collision. Astronomers can see that gas as a bright X-ray glow sitting between the two clusters. They can also map the mass distribution using gravitational lensing. And the mass is not where the gas is. The mass is out ahead of the gas, sitting with the galaxies that have already passed through the collision. The dark matter halos around the galaxies did not collide the way the gas did. They passed right through each other because dark matter does not interact with itself the way ordinary matter does. The result is a clean separation, visible matter in the middle, dark matter on the sides. The lensing maps show two distinct clumps of mass, and the light from the galaxies shows two distinct populations. But the gas, the stuff that glows in X-rays, is sitting in between. The bullet cluster is direct visual evidence that most of the mass in galaxy clusters is not the stuff we can see, it is something else. So, what is dark matter? The short answer is nobody knows. The long answer is that physicists have a lot of ideas and none of them have been confirmed. The simplest possibility is that dark matter is just ordinary matter that happens to be dark. Brown dwarfs, failed stars too small to ignite fusion, rogue planets drifting through interstellar space, black holes, neutron stars, cold gas clouds. All of that stuff exists, and none of it emits much light. Maybe there is a lot more of it than we realize, scattered through the halos of galaxies, adding up to the missing mass. Astronomers call this category massive compact halo objects, MACHOs. The name is a joke. A response to an earlier proposal that dark matter might be weakly interacting massive particles, WIMPs. MACHOs versus WIMPs. The field has a sense of humor. The MACHO idea does not work. Surveys looking for gravitational microlensing, the brief brightening of a background star when a massive object passes in front of it, have put tight limits on how many MACHOs can be floating around in the halos of galaxies. There are some. Brown dwarfs exist. Rogue planets exist. But there are not enough of them to account for the missing mass, not even close. And there is another problem. Ordinary matter, the kind made of protons and neutrons and electrons, leaves a signature in the cosmic microwave background. The density of ordinary matter affects how the early universe evolved, how the density fluctuations grew, how the first structures formed. The cosmic microwave background data is extraordinarily precise, and it pins down the density of ordinary matter to within a few percent. The answer is about 5% of the total mass energy of the universe. Everything made of atoms, every star, every planet, every grain of dust, every human, adds up to 5%. The dark matter that shows up in galaxy rotation, curves and gravitational lensing makes up about 27%. That is more than 5 times as much. Dark matter cannot be ordinary matter. It has to be something else. The leading candidate is a new kind of particle, something that was produced in enormous quantities in the early universe, something that interacts only through gravity and possibly through the weak nuclear force, and something that is stable enough to still be around today. The particle has not been discovered yet. Physicists do not know its mass, its spin, or any of its properties, except that it has to be massive enough to clump together gravitationally, and it has to interact weakly enough that it has not shown up in any detector yet. WIMPs fit the bill. They are predicted by certain extensions of the standard model of particle physics, theories that add new particles and new forces to explain phenomena the standard model does not cover. If WIMPs exist, they were created in the hot, dense conditions of the early universe, and they should still be zipping through space today, including through Earth. Billions of them passing through your body every second. They do not interact with ordinary matter, so they pass right through. No collisions, no energy transfer, no signal, except very rarely. If a WIMP happens to hit a nucleus in just the right way, it might transfer a tiny bit of energy, creating a detectable signal. That is what physicists are looking for. Dozens of experiments around the world have been built to detect dark matter particles. Most of them are buried deep underground to shield them from cosmic rays and other background radiation that could create false signals. They use tanks of ultra-pure xenon or germanium or other materials, cooled to near absolute zero, monitored by sensitive detectors that can pick up the tiny flash of light or the faint vibration that would be produced if a dark matter particle collided with a nucleus. The experiments have been running for decades. They have not found anything. The sensitivity keeps improving. The background noise keeps dropping. The experiments rule out larger and larger swaths of the parameter space where WIMPs might exist, but no detection. Either WIMPs do not exist, or they interact even more weakly than the models predict, or they are much lighter or much heavier than anyone expected. Other candidates are being explored. Axions, hypothetical particles originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. Axions are much lighter than WIMPs, possibly 1,000,000 times lighter, and they would behave differently. Instead of clumping into halos around galaxies, they might form a diffuse cloud filling the entire galaxy, condensing into a state called a Bose-Einstein condensate. Detecting axions requires different experiments, ones that look for the way axions would interact with strong magnetic fields, converting into photons under the right conditions. Sterile neutrinos, another candidate, would be heavier cousins of the known neutrinos, particles that barely interact with anything. Primordial black holes, tiny black holes formed in the first moments after the Big Bang, could account for some of the dark matter if they exist in the right mass range. None of these ideas have been confirmed. The experiments are ongoing. The search continues. And after decades of looking, physicists are starting to ask whether dark matter is a particle at all. Maybe the problem is not that we have not detected dark matter. Maybe the problem is that dark matter does not exist. Maybe gravity behaves differently on large scales than Einstein's equations predict. This idea is called modified Newtonian dynamics, MONAD, and it has a small but dedicated following. MONAD proposes that the force of gravity is slightly stronger than Newton's law predicts when the gravitational acceleration is very weak, which is exactly the regime you find in the outer regions of galaxies and in galaxy clusters. Tweak the equations in just the right way, and you can reproduce the flat rotation curves without invoking dark matter. You can explain Zwicky's galaxy clusters and Rubin's galaxies with ordinary matter and modified gravity. The problem is that MONAD does not work everywhere. It fits some observations and fails others. It cannot explain the bullet cluster. It cannot explain gravitational lensing. It cannot explain the cosmic microwave background. Every time someone tweaks the theory to fit one set of observations, it breaks somewhere else. Dark matter, for all its mystery, fits everything. MONAD does not. Most physicists have concluded that MO-NAD is wrong and dark matter is real. They just have to figure out what it is. And then there is dark energy, a different problem entirely. Not invisible matter, but invisible energy. Something that fills all of space, exerting a kind of negative pressure, pushing space apart. Dark energy was discovered in the late 1990s by two independent teams studying distant supernovae. Type 1a supernovae, the exploding white dwarf stars that serve as standard candles for measuring cosmic distances. The teams were trying to measure how fast the expansion of the universe was slowing down. Everyone knew the universe was expanding. Hubble had proved that in the 1920s. Everyone also assumed the expansion was slowing down because gravity pulls everything together. The question was how fast it was slowing. The supernova data would give the answer. Measure the distances to very distant supernovae, compare them to how fast those galaxies are receding, and you can calculate the deceleration rate. Both teams did the measurements. Both got the same result. The expansion is not slowing down, it is speeding up. That should not be possible. Gravity is attractive. It pulls things together. It slows the expansion. There is nothing in the standard model of cosmology that makes the expansion accelerate unless you add something new. Something with negative pressure. Something that does not clump into galaxies or clusters, but spreads uniformly through space, filling every cubic centimeter with a constant energy density. As space expands, more space is created, and more of this energy appears. The energy density stays constant even as the total volume grows. That drives the acceleration. The more space there is, the more dark energy there is, and the faster the expansion becomes. This is not science fiction. This is what the supernova data requires. The discovery won the Nobel Prize in Physics in 2011. And it opened a hole in cosmology that has not been closed. Dark energy makes up about 68% of the total mass energy content of the universe. Dark matter is 27%. Ordinary matter, the stuff that makes up stars and planets and you, is 5%. The universe is dominated by things we do not understand. 2/3 of it is dark energy. A little more than a quarter is dark matter. Everything we can see, every galaxy, every star, every atom is a rounding error. A thin film of visible matter floating on an ocean of invisible stuff. That is the universe we live in. And we do not know what most of it is made of. The simplest explanation for dark energy is the cosmological constant, the term Einstein added to his equations in 1917 to make the universe static, and then removed after Hubble showed the universe was expanding. Einstein called it his greatest blunder, except it turns out the cosmological constant might be real. In quantum field theory, empty space is not actually empty. It is filled with fluctuating fields, virtual particles popping in and out of existence, a seething foam of quantum activity at scales far too small to observe directly. That activity has energy, and if space has energy, it should have pressure. The math predicts that the energy of empty space, the vacuum energy, should act exactly like a cosmological constant. It should push space apart, driving the accelerated expansion. The problem is the number. When physicists calculate how much vacuum energy there should be, the answer is absurdly large. 10 to the power of 120 times larger than the observed value. That is not a typo. The theoretical prediction overshoots the observation by a factor of 1, followed by 120 zeros. It is the worst prediction in the history of physics, and no one knows why. Maybe the calculation is wrong. Maybe vacuum energy does not contribute to the cosmological constant the way quantum field theory predicts. Maybe there is some mechanism that cancels most of it out, leaving only the tiny fraction we observe. No one has found such a mechanism. Or maybe dark energy is not a cosmological constant at all. Maybe it is a field, something dynamic that changes over time, something that was weaker in the past and is getting stronger now. Physicists call this idea quintessence. If quintessence is real, the acceleration of the universe is not constant, it is changing. And if it is changing, we might be able to measure that change by observing how the expansion rate has evolved over cosmic history. So far, the data is consistent with a cosmological constant. The acceleration looks constant, but the error bars are large enough that quintessence is not ruled out. The observations are improving. Future surveys, mapping millions of galaxies and supernovae across vast distances, will narrow down the possibilities. Either dark energy is a cosmological constant, a fixed property of space itself, or it is something stranger, something that evolves, something with its own dynamics. Both options are uncomfortable. A cosmological constant raises the question of why the value is what it is. Why is it so small compared to the theoretical prediction, but still large enough to dominate the universe today? Why did dark energy only start driving the acceleration a few billion years ago, when the universe had expanded enough that the matter density dropped below the dark energy density? The timing is suspicious. It looks fine-tuned, like the universe was set up to have this particular balance at this particular moment in cosmic history. Some physicists argue that this is evidence for the multiverse. In a multiverse with infinitely many bubble universes, each one with a different value of the cosmological constant, only the bubbles where the value is small enough to allow galaxies and stars to form will have observers. We find ourselves in such a bubble not because it is special, but because we could not exist in a bubble where the cosmological constant was much larger. This is called the anthropic principle. It explains the fine-tuning by appealing to selection bias. The argument is controversial. It does not predict the value of the cosmological constant. It just says we should not be surprised that it is in the range compatible with life. Some physicists find that satisfying. Others find it deeply unsatisfying. Quintessence does not solve the problem. It just shifts it. Instead of asking why the cosmological constant has the value it does, you are asking why the quintessence field has the properties it does. Why does it have the right energy density? Why does it vary in time in just the right way to drive the acceleration we observe? The questions do not go away, they just get reframed. And there is a third possibility that no one likes to talk about. Maybe general relativity is wrong. Not wrong in the sense that it fails in the solar system or near black holes. It works there. Wrong in the sense that it does not correctly describe the behavior of space on cosmological scales. Maybe the equations break down when you try to apply them to the entire universe. Maybe there is a modification, a correction term, something that only becomes important over distances of billions of light years. That modification could mimic the effects of dark energy without requiring any new substance filling space. The problem is that no one has found a modification that works. Every attempt to tweak general relativity to eliminate the need for dark energy ends up breaking something else. The theory predicts gravitational waves, which we have detected. It predicts the bending of light around massive objects, which we have observed. It predicts the precession of Mercury's orbit, which matches the data perfectly. General relativity works. Changing it is not easy, and changing it in a way that explains dark energy without breaking everything else has so far proved impossible. So where does that leave us? With two enormous gaps in our understanding. Dark matter, making up 85% of the matter in the universe, and dark energy, making up 68% of the total mass energy. Together, they account for 95% of the universe. The stuff we can see, the stuff we understand, the stuff that makes up stars and planets and people, is 5%. A trace component, an afterthought. The universe is not made of atoms. Atoms are what is left over after you account for the dark stuff. That is the humbling reality of modern cosmology. We have mapped the observable universe. We have traced its history back to a fraction of a second after the Big Bang. We have found galaxies at the edge of time and measured the faint glow of the cosmic microwave background to extraordinary precision. And we still do not know what most of the universe is made of. We know it is there. We can measure its effects. We can map its distribution. But we do not know what it is. The search continues. Experiments deep underground are still looking for dark matter particles. Telescopes are still surveying distant supernovae to pin down the properties of dark energy. Theorists are still building models, running simulations, trying to find an explanation that fits all the data. Progress is being made, slowly. The parameter space for WIMPs is shrinking. The measurements of the cosmological constant are getting more precise. The observations are piling up, but the answers are not here yet. And there is a real possibility that the answers will not come from the current generation of experiments. That dark matter particles, if they exist, interact too weakly to be detected with current technology. That dark energy is exactly a cosmological constant, and there is no deeper explanation for its value. That the universe is simply built this way, and the only reason we can give is that if it were built any other way, we would not be here to ask the question. That would be an unsatisfying conclusion. Science is supposed to explain things. It is supposed to reduce the number of mysteries, not just catalog them. Dark matter and dark energy are not small mysteries. They are not loose ends that need tidying up. They are fundamental gaps in the picture. The scaffolding on which galaxies are built is invisible. The force driving the expansion of space is unexplained. We are living in a universe where the majority of the content is unknown, not unobserved, not poorly understood, unknown. We do not even know what kind of thing dark matter is. Particle, field, modification of gravity, all of the above? None of the above? The same is true for dark energy. Cosmological constant, quintessence, modified gravity, quantum vacuum, measurement error. The list of possibilities is long, and the evidence is ambiguous. And yet the universe works. Galaxies rotate, clusters stay bound, space expands. The cosmic microwave background has the structure it has. The large-scale structure of the universe matches the predictions. The supernovae behave the way they should. Everything fits, not perfectly. There are tensions, small discrepancies between different measurements. The Hubble constant problem. The impossibly early galaxy's web is finding. The details that do not quite line up, but the overall picture holds. Dark matter and dark energy, whatever they actually are doing their jobs. The universe is functioning according to rules that include them. We just do not know what the rules are yet. We are mapping a territory where most of the landmarks are invisible, where the terrain is hidden under a fog that does not lift no matter how bright a light we shine, where the only way forward is to feel our way carefully, step by step, inferring the shape of the ground from the way visible things move across it. That is the situation. 95% of the universe is dark, unknown, beyond the reach of direct detection, and the 5% we can see, the galaxies and stars and planets and people, are just the visible part of a much larger structure, a thin, bright layer floating on an invisible foundation. The cosmos is not what it appears to be. It is not made of the stuff we understand. It is made mostly of something else. And until we figure out what that something else is, the universe remains a mystery, a very well-mapped mystery, a mystery with precise measurements and detailed observations, but a mystery nonetheless. This is the uncomfortable place modern cosmology finds itself. We know more about the universe than any previous generation. We can see farther, measure more precisely, test theories with greater rigor, and yet the most basic questions, what is the universe made of? Why is it structured the way it is? What forces are shaping its evolution remain unanswered. The edge of the observable universe is 46.5 billion light-years away. The part beyond that edge may stretch forever, and even the part we can see is mostly invisible. That is the reality. The universe is vast, ancient, and profoundly strange, and we are only beginning to understand it. The journey to the edge is not over. It has barely started, because the edge is not a place. It is a limit of knowledge, and every time we push that limit back, we find more questions waiting on the other side. But the questions are not just about distant galaxies and invisible matter. They are also about us, about where we fit into this vast, strange cosmos, about what it means to be a small, finite creature looking out at an infinite universe, about whether the search for answers is worth the effort when the answers keep receding into the distance. That is where the final chapter goes, not outward, but inward, not to the edge of space, but to the edge of meaning, to the place where cosmology meets philosophy, where the scale of the universe forces a confrontation with the scale of human existence, where the journey to understand everything out there becomes a journey to understand what we are doing here. We have spent the last 7 chapters staring into the dark, watching Webb pull galaxies out of the first few 100 million years after the Big Bang, counting 10,000 galaxies in a patch of sky the size of a pinhead, following the Voyagers as they crossed the heliopause and entered the space between stars, tracing the invisible scaffolding of dark matter holding the universe together, measuring the acceleration of space driven by dark energy we cannot see or explain. We have traveled from the cosmic microwave background, the oldest light in the universe, to the heliopause, the edge of the sun's bubble, from the Kuiper belt to the Oort cloud to the interstellar void, from galaxies 13 billion light-years away to structures so large they span hundreds of millions of light-years. We have pushed outward in every direction, following light backward through time, mapping the observable universe from edge to edge. And now we turn around, not to look at something closer, not to zoom in on some smaller detail we missed, but to ask a different kind of question, not what is out there, but what does it mean that we can see it at all? What does it mean that a species of primates on a small rocky planet orbiting an unremarkable star in the outer suburbs of an ordinary galaxy has built instruments sensitive enough to detect photons that have been traveling for more than 13 billion years? What does it mean that we can map the structure of the universe, trace its history back to the first fraction of a second, measure the composition of distant stars, and calculate the distances to galaxies so far away that their light left before Earth even existed? What does it mean that we are here, now, at this particular moment in cosmic history, looking outward and asking why? The scale of the universe is incomprehensible. That is not a poetic exaggeration, it is a statement of fact. The human brain did not evolve to grasp distances measured in billions of light-years. We evolved to navigate a world measured in meters, to judge whether a predator is close enough to be dangerous, to estimate how far we need to throw a rock to hit a target, to recognize faces at a distance of a few dozen feet. Our spatial reasoning tops out somewhere around the scale of a landscape, a valley, a mountain range, maybe the horizon if the weather is clear. Beyond that, numbers stop meaning anything. 1 million is already abstract. 1 billion is nonsense. 1 trillion is just a word, and the universe does not deal in trillions. It deals in numbers so large that even scientific notation starts to feel inadequate. The observable universe is 93 billion light-years across. That number does not fit in a human mind. You can say it, you can write it down, you can use it in a calculation, but you cannot visualize it. You cannot hold it in your head the way you can hold the image of a room or a city or even the curve of the Earth from orbit. It is too big. The gap between human scale and cosmic scale is so vast that no analogy bridges it cleanly. If you shrunk the observable universe down so that the Earth was the size of a grain of sand, the observable universe would still be larger than the actual observable universe. The math does not help. The metaphors do not help. The scale is inhuman, and yet we keep measuring it. Why? Why does it matter how far away the farthest galaxy is? Why does it matter what happened in the first few 100 million years after the Big Bang? Why does it matter whether the universe is infinite or finite, whether it will expand forever or collapse back on itself, whether dark matter is a particle or a modification of gravity? None of it affects your life. None of it changes the fact that you woke up this morning, that you have things to do today, that the people you care about are still here, that the sun still rises and the seasons still turn. The universe is vast and strange and mostly empty, and it will keep being vast and strange and mostly empty whether you understand it or not. So why try? Because we are the kind of creature that tries. That is the answer. Not a satisfying answer, maybe, not a deep philosophical insight. Just a fact. Humans are curious. We want to know things. We want to understand how the world works, even when the world is too large to affect us and too distant to visit. We build telescopes not because we need to, but because we can. Because the question is there, because the light is arriving and we have the tools to decode it. Because someone, at some point, looked up at the night sky and wondered what those faint smudges of light were, and that question led to another question and another, and eventually to Hubble and Webb and a detailed map of the observable universe stretching back to the beginning of time. The process took centuries. Galileo pointed a telescope at the sky in 1609 and saw moons orbiting Jupiter, proving that not everything in the heavens revolved around Earth. William Herschel mapped the Milky Way in the late 1700s and realized it was a flattened disk of stars, not a uniform sphere. Edwin Hubble measured the distances to other galaxies in the 1920s and discovered the universe was expanding. Arno Penzias and Robert Wilson stumbled on the cosmic microwave background in 1964 and confirmed the Big Bang. Vera Rubin measured galaxy rotation curves in the 1970s and found the first strong evidence for dark matter. Saul Perlmutter, Adam Rees, and Brian Schmidt discovered the accelerating expansion in the late 1990s and forced cosmologists to confront dark energy. Each discovery built on the ones before it. Each answer raised new questions, and the questions kept getting bigger. The tools got better. Telescopes got larger. Detectors got more sensitive. Computers got faster. Space missions became possible. Hubble launched in 1990 and spent 3 decades mapping the universe in visible and ultraviolet light. Planck launched in 2009 and mapped the cosmic microwave background with extraordinary precision. Webb launched in 2021 and opened the infrared universe, revealing galaxies too distant and too faint for Hubble to see. The Voyagers launched in 1977 and are still sending data from beyond the heliopause, more than 47 years later. Every mission, every telescope, every detector, every observation added another piece to the picture, and the picture that emerged is not simple. It is not clean. It is not the kind of cosmos that fits comfortably into human intuition. It is strange, vast, mostly invisible, and utterly indifferent to whether we understand it. And yet we keep trying. That persistence is worth noticing. Science is not easy. Discovery is not inevitable. Building a telescope that can detect galaxies 13 billion light-years away requires solving thousands of engineering problems. You need a mirror large enough to collect enough light. You need detectors sensitive enough to register individual photons. You need a spacecraft that can survive the temperature swings of space, the radiation environment, the vibrations of launch. You need a way to point the telescope with enough precision that it stays locked on a target for hours or days, while the spacecraft is moving and the Earth is rotating and the stars are drifting. You need a way to send the data back across millions of kilometers of space, encode it in radio signals and decode it on the other end without losing information. You need funding. You need international cooperation. You need teams of engineers and scientists working for decades to design, build, test, launch, and operate the mission. And you need all of that to work perfectly, because if the mirror is misaligned by a fraction of a millimeter, or the instruments fail, or the software has a bug, the mission fails. The investment is wasted. The questions go unanswered. Hubble almost failed. When it launched in 1990, the first images it sent back were blurry. The mirror had been ground to the wrong shape, a mistake so small it was measured in microns, but large enough to ruin the telescope's vision. The mission looked like a disaster. Then NASA sent astronauts to install corrective optics, essentially a pair of glasses for the telescope, and Hubble's vision cleared. The deep fields came later. The discoveries came later. The mission succeeded because people refused to give up on it. That kind of persistence is not unique to Hubble. It is the norm in science. Experiments fail, missions get delayed, instruments break, funding runs out. And the work continues anyway because the questions matter. Not in a practical sense, not in a way that pays the bills or solves immediate problems, but in the sense that understanding the universe is part of what makes us human. The drive to know is not optional, it is built in. And the things we have learned are extraordinary. We know the universe is 13.8 billion years old. We know it began in a hot, dense state and has been expanding ever since. We know it is flat, or very close to flat, which means it could be infinite. We know it is filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. We know the first stars formed a few 100 million years after the Big Bang. We know galaxies assembled over billions of years through mergers and accretion. We know dark matter exists and makes up most of the mass in the universe, even though we do not know what it is. We know dark energy exists and is driving the accelerating expansion, even though we do not know what it is. We know the cosmic microwave background is the oldest light in the universe, a snapshot of the cosmos when it was 380,000 years old. We know the Sun is just one star among hundreds of billions in the Milky Way, and the Milky Way is just one galaxy among hundreds of billions in the observable universe. We know Earth is not the center of anything, not the center of the solar system, not the center of the galaxy, not the center of the universe. We are sitting on a small planet orbiting a medium-sized star in the outer regions of a spiral galaxy that is itself part of a galaxy cluster, that is itself part of a supercluster, that is itself part of the cosmic web stretching across billions of light years. We are not special. We are not central. We are not the point. And yet we are the ones asking the questions. That is the paradox at the heart of cosmology. The universe is vast, ancient, and mostly indifferent to life. But life exists anyway. Consciousness exists anyway. Intelligence exists anyway. And intelligence, for reasons that are still not fully understood, is driven to understand the world around it, to map the cosmos, to trace its history, to ask where it came from and where it is going, to build instruments that can detect the faintest signals from the farthest distances and decode them into knowledge. The universe does not care whether we understand it, but we care. And that caring, that relentless curiosity, is what has taken us from wondering about the stars to measuring the edge of the observable universe. The humbling part is how much we still do not know. Dark matter and dark energy are the obvious gaps. Together, they make up 95% of the universe, and we do not have a confirmed detection of either one. We can map their effects. We can measure how dark matter clumps around galaxies and how dark energy drives the expansion, but we do not know what they are. We do not know if dark matter is a particle or a field or a modification of gravity. We do not know if dark energy is a cosmological constant or a dynamic field or a sign that general relativity breaks down on large scales. The tools we have are powerful, but they are not powerful enough to close those gaps. The experiments are running, the data is coming in, but the answers are not here yet, and there is a real possibility that the answers will not come from the current generation of instruments, that we will need a new idea, a new approach, a new technology before we can solve the mysteries that dominate the universe. The same is true for the early universe. Webb is finding galaxies that are too massive, too bright, too mature for their age. The models say galaxies should have taken longer to form. The data says they formed faster. Something is wrong. Either the models are missing a piece of physics, or the observations are being misinterpreted, or the early universe was stranger than anyone expected. The tension has not been resolved. The data is still coming in. The models are being refined. But the gap is real, and it is forcing cosmologists to reconsider assumptions they thought were solid. That is how science works. You build a model, you test it. The model breaks, you fix it or replace it. The process is messy, it is slow, it is frustrating, and it is the only way forward. But the messiness is not a failure, it is a feature. Science is not about knowing everything. It is about narrowing the range of what we do not know. Every observation rules out some possibilities and opens up others. Every measurement refines the parameters of the models. Every discovery adds a new piece to the puzzle. The picture is incomplete. It will always be incomplete, but it is getting clearer. The edges are sharper. The details are finer. The map of the universe we have today is vastly more detailed and more accurate than the map we had a century ago. And the map we will have a century from now will be vastly better than the one we have today. The work continues. The questions pile up. The instruments get better. And slowly, piece by piece, the universe reveals itself. There is something profoundly human about that process. We are small. We are finite. We live on a tiny planet in a vast, indifferent cosmos. We have no special status, no central location, no guarantee that we will survive long enough to answer all the questions we are asking. And yet we build telescopes anyway. We launch spacecraft anyway. We spend billions of dollars and decades of effort to measure things that will never affect us in any practical way. We do it because we can. Because the questions are there, because understanding the universe is part of what it means to be human. The drive to know is not rational. It does not increase your lifespan or improve your odds of survival. It is just part of who we are. A species that looks up and wonders, and the wonder is justified. The universe is extraordinary, not because it was designed for us, not because it has meaning or purpose built into it, but because it exists at all, because the laws of physics allow stars to form and galaxies to assemble and planets to coalesce and life to emerge, because the conditions in the early universe were just right to produce the structures we see today, because the expansion rate is just slow enough that gravity could pull matter together into galaxies, but just fast enough that the universe did not collapse back on itself billions of years ago. Because the fundamental constants, the masses of particles, the strengths of forces, the value of the cosmological constant, all fall in a narrow range where complexity is possible. Step outside that range, and the universe is sterile. Too much dark energy, and galaxies never form. Too little, and the universe collapses. Too much electromagnetic force, and atoms do not hold together. too little, and chemistry does not work. The universe we observe is balanced on a knife edge. Change any of the constants by a small amount, and stars do not shine, planets do not form, life does not emerge. We exist in a universe where the rules allow us to exist. That is not an explanation, it is just a fact. A strange, unsettling, remarkable fact. Some physicists argue this is evidence for a multiverse, that there are countless bubble universes with different constants, different rules, different outcomes, and we find ourselves in one of the rare bubbles where the constants allow complexity because we could not exist in any of the others. The anthropic principle. We are here because if we were not, we would not be asking the question. That argument is controversial. It does not predict anything. It just says we should not be surprised that the universe is the way it is, because if it were any other way, we would not be here to notice. Some find that satisfying, others find it a cop-out. The debate is ongoing. The data does not settle it. The universe is what it is, and we are still trying to figure out why. But the question itself is a privilege. The fact that we can ask why the universe has the constants it has, why galaxies formed, why the expansion is accelerating, is a triumph. A century ago, we did not know the universe was expanding. 2 centuries ago, we did not know other galaxies existed. 5 centuries ago, we thought the Earth was the center of everything. We have come an extraordinary distance in a very short time. The pace of discovery has been accelerating. Hubble launched in 1990, Planck launched in 2009, Webb launched in 2021. The gap between missions is shrinking, the tools are getting better, the data is piling up, and the picture of the universe is sharpening faster than any previous generation could have imagined. That progress is not guaranteed. Science requires funding, infrastructure, international cooperation, political stability, and a society that values curiosity and long-term thinking. All of those things are fragile. Missions get cancelled, budgets get cut, priorities shift. There is no law of nature that says humanity will continue exploring the cosmos indefinitely. We could stop, we could turn inward, we could decide that the questions are not worth the cost. And if we do, the light from distant galaxies will keep arriving, and no one will be here to measure it. The universe will go on without us. It always has. It always will. We are passengers, not drivers. The cosmos does not need us to understand it, but we need to understand it. Because the act of understanding, the process of asking questions and building instruments and testing theories and refining models, is what makes us more than just biological machines replicating and consuming. It is what gives meaning to existence in a universe that has no built-in meaning. We are the universe trying to understand itself. That is not a metaphor. That is literally what is happening. The atoms in your body were forged in stars, the calcium in your bones, the iron in your blood, the oxygen you are breathing. All of it came from supernova explosions billions of years ago. You are made of stardust, and now that stardust has organized itself into a form capable of looking back at the stars and asking where it came from. The answer, as far as we can tell, is chance. There is no plan, no design, no purpose embedded in the fabric of reality. The universe is the way it is because the laws of physics play out the way they do. Stars form because gravity pulls gas together. Galaxies assemble because dark matter clumps and ordinary matter falls into the wells. Planets coalesce from the debris left over after star formation. Life emerges when chemistry gets complicated enough to replicate itself. Intelligence arises when evolution favors brains capable of predicting the future and modeling the world. And curiosity, the drive to understand, is just a side effect of having a brain powerful enough to ask questions. None of it is inevitable. None of it is guaranteed. It just happened. And now that it has happened, now that we are here, we find ourselves looking outward and asking what it all means. The answer, if there is one, is not out there in the galaxies. It is here, in the act of looking. In the decision to build a telescope and point it at the sky and wait for the light to arrive. In the patience required to collect data for years or decades. In the stubbornness required to keep going when the experiments fail and the funding runs out and the answers do not come. In the collaboration required to bring together scientists from dozens of countries to work on a single mission. In the humility required to accept that most of the universe is invisible and most of what we think we know might be wrong. In the hope that the next observation, the next mission, the next generation of instruments will bring us closer to understanding. That is where the meaning is. Not in the destination, in the journey. The voyagers are still traveling. Right now, as you are reading this, they are moving outward at more than 50,000 kilometers per hour. They have crossed the heliopause. They are in interstellar space. The sun is just another star in the sky. The planets are invisible. The spacecraft are alone in the dark, billions of kilometers from anything, and they are still sending data, still measuring the plasma density, the magnetic field strength, the cosmic ray flux, still doing science. The power is fading. The instruments are shutting down one by one. In another decade, maybe two, the transmitters will stop. The signals will end. The voyagers will go silent, but they will keep moving for tens of thousands of years, for hundreds of thousands of years, for millions of years. Drifting through the galaxy, carrying a golden record with sounds and images from Earth, a message from a species that existed once and wondered if anyone else was out there. The odds of the record ever being found are vanishingly small. It does not matter. The message was not really for aliens. It was for us. A statement that we were here, that we looked up, that we tried. Webb is still observing. Hubble is still observing. Ground-based telescopes are still observing. Experiments deep underground are still searching for dark matter particles. Satellites are still mapping the cosmic microwave background. The work continues. The questions pile up. The data comes in. And piece by piece, observation by observation, the universe reveals itself. Not all at once, not in a sudden flash of insight. Slowly, patiently, the way a photograph develops in a dark room. The outlines first, then the details, then the fine structure. The picture is not complete. It will never be complete, but it is getting clearer. That is the story, not the edge of the universe, not the farthest galaxy, or the oldest light, or the size of the observable cosmos. Those are just data points. The story is the drive to find them. The decision to build instruments that can detect photons from 13 billion years ago. The willingness to spend decades staring at a single patch of sky. The stubbornness to keep looking when the answer is not there. The humility to admit when the models are wrong. The collaboration required to pool knowledge from hundreds of scientists across dozens of institutions. The hope that the next observation will bring us closer to understanding. That is the story, and it is a human story. A story about what we are capable of when we decide that understanding the universe matters. The universe is vast. We are small. The universe is ancient. We are brief. The universe is mostly invisible. We can see only a fraction of it. But the fraction we can see is enough. Enough to trace the history of the cosmos from the Big Bang to the present. Enough to map the distribution of galaxies across billions of light years. Enough to measure the expansion rate and infer the presence of dark energy. Enough to detect the gravitational pull of dark matter and know that most of the universe is made of something we do not understand. Enough to realize that the observable universe is just a tiny piece of a much larger whole. Enough to know that we are not the center. not the point, not the reason any of this exists, and enough to know that we are here anyway, looking outward, asking questions, building telescopes, launching spacecraft, mapping the cosmos, touching forever, and in the process, finding ourselves. So this is where it ends, or maybe where it begins. 46 billion light-years in every direction. A sphere of space containing hundreds of billions of galaxies, each filled with hundreds of billions of stars, stretching across a gulf so vast that light itself, the fastest thing there is, takes more than 13 billion years to cross it. And beyond that sphere, more, possibly infinitely more. Galaxies we will never see, stars that will never register on any detector we build, planets where light from Earth will never arrive because the expansion of space is carrying them away faster than our signals can reach them. The universe goes on. And we are here on a small planet orbiting an ordinary star, pointing telescopes at the sky and measuring things that have no practical effect on our lives whatsoever. That is the strange part. Not the scale, not the distances, not the fact that most of the universe is invisible or that we do not know what it is made of. The strange part is that we care, that a species of primates built instruments sensitive enough to detect photons that have been traveling since before the sun existed, that we mapped the cosmic microwave background, traced the history of galaxy formation, discovered dark matter and dark energy, and kept going even when the answers raised more questions than they solved. The universe does not need us to understand it. It was doing just fine for 13.8 billion years before we showed up. But we need to understand it, because the act of looking outward, of asking what is out there and how it works and where it came from, is what makes us human. We are the universe looking back at itself, and the view, incomplete and puzzling as it is extraordinary. The edge is not a place. It is a question, and the question is still open. Keep looking, because each new wavelength and deeper survey can illuminate our small window, even when the ultimate horizon remains beyond sight.